Uh, yeah. Good evening, sir. How are you?
Good evening, good evening. Today there
Yeah.
is some puja time, no Sivaratri, I saw it, and I got stuck there.
No worries, sir. No worries.
Yeah,
Uh, sir, can we start?
yeah, now I'm ready.
Okay. So, Ishika, you can take it forward.
Good evening, everyone. A warm welcome to the day 3 of 6-day online ATAL faculty development program on vacuum technology in semiconductor manufacturing and packaging, innovations, applications, and challenges, organized by the North Cap University, Gurugram. As we progress further in this program, we continue to uncover the vast impact of vacuum technology in semiconductor manufacturing. Yesterday, on day 2, we explored two highly significant topics: thermal evaporation in clean room and thin film deposition techniques under vacuum conditions. In yesterday's session, led by Professor J.P. Singh, provided an in-depth understanding of thermal evaporation processes, highlighting the importance of clean room environments, material selection, and deposition techniques used in high-precision semiconductor fabrication. The session emphasized how maintaining contamination-free conditions and process control is critical for achieving high-quality thin films. Following that, Dr. C. Ramachandra took us through the complexities of thin film deposition techniques under vacuum conditions. He explained various deposition methods, including sputtering and evaporation, detailing how vacuum conditions influence film quality, adhesion, and overall device performance. His insights bridge the gap between fundamental science and industrial applications, providing valuable perspectives on advanced thin film manufacturing.
As we move forward, today's sessions will take us deeper into the design and application of vacuum chambers and the role of vacuum technology in IC fabrication. We have an exciting lineup of expert speakers who will share their insights with us. Their expertise will help us understand the technical advancements and industrial challenges shaping the future of semiconductor manufacturing. Let, let's begin day 3 with enthusiasm, curiosity, and a shared commitment to learning.
As we move forward, our next session focuses on vacuum chambers and system design, a crucial component in semiconductor manufacturing. We are honored to welcome Professor V.V. Rao, a renowned expert in vacuum science and technology with decades of experience in vacuum system design and industrial applications. A visiting professor at IIT Tirupati and former professor at IIT Kharagpur, he has significantly contributed to advancing vacuum technology research and industry practices. His work focuses on designing and optimizing vacuum systems for semiconductor applications, ensuring precision, efficiency, and scalability in manufacturing. Today, he will provide insights into vacuum chamber construction, offering valuable insights into both academic research and industry best practices. Without further ado, we invite Professor V.V. Rao to take the virtual stage and share his expertise with us.
Thank you, sir. Kindly make the
Welcome,
presentation.
sir.
You have to make the presentation, share them. Yeah,
Sir, is the screen visible?
yes, for me it is visible. For them, I hope it's okay.
Yeah, it is visible for everyone. Yeah.
Okay. So other day we were discussing about the basic concepts like mean free path, time to form monolayer, and varieties of concepts and units of vacuum. And then we have seen that it is very important for a system design people to understand what type of chambers that we have to make, how to connect it to the pump, and depending on the application, what specific requirements we have to focus and concentrate. So at that time, I was discussing last class already, when a system is connected by a pump, you inevitably have got a connecting pipe. So when system may be very costly, it may be a ultra high vacuum system with electron beam depositions and chemical vapor deposition, physical vapor depositions, or ion beam etching facilities, or analytical instruments, all of them together, several vacuum boxes, they are all together forming a system mutually connected with robotic arms compatible to vacuum, etc. But all these things are connected. They are not called chambers, they are vacuum chambers. So pumps have to be connected. But these pumps are relatively noisy, oily, and they have got their own problems. It's not like a chamber. So you require a connecting pipe. And it is often required to, for the convenience, to have sufficiently flexible pipe, sufficiently long with some bends, etc., so that the pump is little bit away from the system, but it's doing its duty of evacuation. And then we try to do evaporation, thin films, etching in our own way. And depending on the particular operation, we isolate the remaining things, etc., etc. This is what has been discussed in the last three sections for all of you. Today, here in this slide, we have to get a feel of a flow rate of vacuum. What is after all happening when you are evacuating? The molecules are removed by the pump through the connecting pipe. How the molecules understand? Because initially everything is at atmospheric pressure. So when I suck the gas that is nearer to the pump, when it is getting sucked, that gives a viscous drag to the next layer like that. All the way the communication is there for the transfer of gas. I would not say molecules because it's an ensemble of gas. Density is quite high at higher pressures. And that way that drag will drag the molecules or gas from the system. Right now, let us understand, let us not worry about semiconductors now, because that has been discussed now. Today, we are talking about vacuum system design. So for me, all that chambers, coating units, analytical instruments, etching, deposition, lithography, everything is a chamber basically. And it has to be maintained in a vacuum. There should not be leaks, there should not be degas, and I should pump it as fast as possible. And if necessary, I should control the pumping capacity so that I can get several equilibrium pressures. Okay, so that depends on the connecting pipe. If there is a pressure drop between the system and the pump, which has to be there, if there is no pressure drop, why should molecules flow from system to the surrounding? System molecules have to be sucked. So left to right in the figure, I've shown red box is the system, the blue box is the pump. And similar things in actually in equivalent way exist in the actual system, like a diffusion pump connected by a rotary pump. Then there is a wall, main isolation wall. Before that, there is a big system, which is also bypassed from the diffusion or turbomolecular pump, because initially you have to evacuate to an acceptable vacuum for the high vacuum pumps. So all that piping network has to be there. And if the pipes are connected in series, then more and more difficulty to pull. So series conductances, they are called pipes, means conductance. They are conducting the flow of the gas. Series conductances, effective conductance can be easily calculated from the electrical network. And if it is a parallel conductance, C is C1 plus C2 plus 3. This is what we have discussed. I am just trying to remind you because in between you have gone through applications. So once you know the conductance is nothing but Ohm's law of vacuum technology is. Ohm's law in electrical engineering is what? Pressure drop is equivalent to potential drop. Current in the electrical circuit is equivalent to mass flow. Their current divided by voltage is given by conductance, electrical conductance. Here, the gas current, the mass flow rate divided by the pressure drop. So that gives you a flow conductance. Okay, that is called C. And once you know the conductance, if it is very high, then the pumping capacity of the pump is totally available at the chamber. But if it is very narrow, if it is a long pipe, you will not get full pumping speed at the site where you have to get vacuum. After all, pump is not sitting in the chamber. Pump is away from the chamber. Okay, and it has to take the help of the connecting pipe. Pump may be crores of rupees, like turbomolecular pumps and cryo pumps. When you have very large systems, tens of such pumps. Similarly, systems are very complicated with with the gold gaskets and lots of high quality walls and different mechanisms to intercouple different chambers for various things. All this high tech stuff is also costly crores of rupees. But these crores of rupees of pumps assembly, crores of rupees of the semiconductor system assembly, when they are connected, only few thousands of rupees of flexible bellows are called flexible pipes. But this fellow will decide the efficiency of the evacuation. If you make a mistake, you can get the vacuum, starting vacuum to start any process, whether it is oxidation or a lithography or an ion beam etching or a doping or a sealing or a soldering, anything. You cannot start at all. It will take 10 days to get the vacuum. If you connect the pump with a small 2 millimeter or 3 millimeter pipe and a long 4 meter pipe, you will not get vacuum. There is no leak, but still it takes time for it to flow through the constricted path. That's why this is a very important point when you do the system design. Lack of time, I will not be able to explain more than this. Next slide, please. So how do you calculate the conductance of the interconnecting pipe? There may be two pipes parallel. There may be two pipes parallel and connected to one pipe singular. Depending on the conveniences, you will have series and parallel connections of various piping network. So entire piping network, like an electrical network that you have done in school days, you can parallel combination, series combination. Totally, you can bring it to a effective resistance or effective conductance. Similarly, here also, you can calculate parallel paths will be C1 plus C2, series path will be 1 by C1. So do all that. And the conductance, effective conductance, if you get, that effective conductance 1 by 3 C plus the manufacturer's pumping speed 1 by S maximum, inverse of that, gives you inverse of the effective pumping capacity available at the site of your semiconductor manufacturing chamber. So this is the system design, one of the most important aspects. So system design from the semiconductor point of view, what material, what is the temperature, that's another game. That's a material science game. That's not vacuum system design. Vacuum system design means what? It should not leak, but it should not degas, and it should be able to be pumped very fast. If necessary, we should control the piping speed, pumping speed, and if whenever it is required, that particular wall should be opened, remaining should not be opened. So this is a logical way of operating pumps, interconnecting pipes, walls, manipulators, all these things together, taking care of no degassing, no unwanted contamination. But wanted contamination is always required. That is called doping. In doping is nothing but wanted contamination. You are actually contaminating pure silicon, but you are contaminating. It's actually p-type impurity. They are called impurities. Okay, that's also contamination, but it is required to make p-type or n-type and make the junctions. Then only you will have a non-linear IV characteristic. You will get diode, transistors, etc. So that is the funda. Okay, so here what we need to worry from the vacuum point of view, I often switch over to semiconductor because the whole conference is for vacuum technology for semiconductor. Oh, well, for to get a feel of it, I keep on transferring to this side to that side, but I am going to focus more on vacuum. Okay. You will find semiconductor lectures quite a bit in these 6 days, quite a bit. So you couple these two things slowly in your own way. If not, you can also later contact me anytime. We can discuss a particular problem or a particular equipment that you may be having or you are planning to have. Anything if you want to decide, I am going to work in a small thin film or a sensor or an ultra high vacuum, not a normal vacuum, whatever you decide. If you tell and your budget or your possible fundings, we can help you. Okay, and even this university can help you. They have got a lot of expertise. This is the way we should do it. The idea of this course is not just to teach you like small kids, because you are all professors, teachers, so you know what is the class teaching anyway. So idea is to plan the laboratories at your respective organizations. Now coming back to this slide, I have explained 1 by S effective plus 1 by S maximum plus 1 by S. So if manufacturer gives, for example, a rotary pump is connected to a chamber. Now, rotary pump fellow manufacturer Hindhevac will tell, sir, my pumping speed is 300 liters per minute. That itself is a function of pressure again. Okay. So now I have connected with a 1 inch, 1 meter pipe below for flexibility. So it has got conductance. Now, it so happened, assume that a conductance of 20 liters per second. How do you know this? Conductance calculations, there are formulae. If you know the diameter, if you know the length, and if you know the average pressure, that means average pressure means pressure in the system is always high, pressure in the pump is always low. Otherwise, there will not be flow of the gases from the system to this. This is a dynamic. Even though there is equilibrium, quasi-static, but it's a dynamic equilibrium. There may be gases coming in, intentional gases like argon, etc. for sputtering. There may be unintentional, but not good gases like leaks, etc. There may be useless degassing, which is giving vapors which are not good. But there may be intentional gases which need to be pumped. Otherwise, if it is flooding, doping will be very high. So doping profiles also need a little bit control by not available, but not making all the impurities available to the site. If necessary, some bit of control has to be made. So all this requirement finally tells us to have a good calculation of conductances and use that conductance in this formula 1 by S effective, 1 by S maximum plus 1 by C. I have given an example. Hindevac has given a pumping speed which varies as a function of pressure, like various pressures. Now, if you carefully observe the table, okay, the conductance is fixed 20 liters, 20 liters like that. Now, if you are purchasing different pumps, okay, different pumps will have different pumping speeds because nominal pumping speed you take from the company and you calculate your conductance. From there, you get the effective pumping speed. What do you do with this effective pumping speed? This is required to make the pressure drop profiles. Pressure will fall first minute, second minute, 10 minute, 15 minute, 100 minute. How it will fall, you can calculate if you know the effective pumping speed, not if you know the actual pumping speed. He may be giving 300 liters per minute, but you are having only 3 liters per minute. If you see the manufacturer's pumping speed versus effective pumping speed, if the conductance of the pipe is very small, then we are in trouble. Or to get a feel of it, for a fixed conductance, I have plotted S effective versus S manufactured. S manufactured will be always maximum pumping speed because he will always quote maximum for getting the order, but we are not getting that. So now you can see that S effective is falling down like anything when the conductance for the same conductance. So either you play with the pumping speed of the manufacturer or you play with the conductance so that you will get the effective pumping speed. Use that effective pumping speed to calculate the effective pump down curve. Next slide, please. The actual calculations can be done by Poiseuille's law because it is a pipe. Pipe, there will be in the higher pressure, it's not very high pressure from atmosphere up to 10 bar. It is more or less like a laminar flow. Laminar flow and viscous flow, both are part of viscous flow only. Viscous flow, viscous turbulent flow, viscous laminar flow. Viscous flow is subdivided into viscous turbulent, viscous laminar. Higher pressures, we normally encounter turbulent flow. In vacuum, even in the right in the beginning, first few seconds, it will be turbulent from 760 torque to maybe 500 torque. Afterwards, when smooth flow is established, it is laminar. It will continue for a typical pipe of 1 inch, etc., up to 1 tar. And after below 1 tar, it is not like a gas flow. They are like molecules. So molecular flow will be there. So here what I have shown is a viscous flow. So these equations are valid up to 10 tar or up to 1 tar because up to 10 tar is called viscous flow. Below zero point 0.1 tar is molecular flow. In between 0.1 to 10 is a transition flow where you will have some attributes of viscous flow as well as molecular flow. So in the worst case, we will just take it as molecular flow. But in the best case, we'll take it as a viscous flow. Viscous flow is better because when we are dragging, it is dragging the other molecules. So it is helping me, the pump, to drag the molecules. First, after all, molecules have to come up to the pump. Then only pump will pump. So viscous drag is a helping hand to the pump through the pipe. Drag is, we are talking with respect to pipe. Pump is left sitting in the right side, left side, this is. So it is a famous Poiseuille's law, mechanical engineers know regularly, pi d4 by 128 eta into a last expression into P average. So if you are evacuating, you might, that average pressure, you take it as 500 tar, 300 tar, 200 tar, like that. At that pressure, you know the viscosity of the air. Mostly we are pumping air only. But if you are pumping hydrogen, like if you are pumping a hydrogen rocket engine, etc., there the viscosity of the hydrogen has to be taken. Then capital D is the diameter of this, and L is the length. If you calculate the C and use that C, use the pumping speed of the manufacturer, 1 by S effective plus 1 by C gives you 1 by S maximum plus 1 by C gives you 1 by S effective. And use that effective pumping speed to measure the pressure versus time curve. That is called pump down curve. Next slide, please. So pump down calculations are done exactly based on this. So you can go through this. I have already explained to you, there is nothing in this. The vessel contains several sources of gases. All those gases have to be removed by the pump. If you look at the right side top figure, I have given so many Qs. These Qs are nothing but loading of the gas. In vacuum, loading means gas. That gas can be intentional gas that we are evaporating in the chemical vapor or physical vapor. That gas can be leaking. That gas can be permeating through the wall. That gases can be evaporating from the light amount of water that may be left over before you close the thing. Okay. So there are several gas leaks. And in addition, initially, you have a lot of gas right in the chamber itself. Because it is at atmospheric pressure, you have connected a pump. Now, before switching on the pump, it is at 760 tar. So, initially, that gas dominates. After some time, when it goes to the 1 tar, etc., the other gases will dominate. The leak rate, degassing rate, evaporation rate, these things will dominate. But initially, the bulk gas that is there in the vessel will be there. Within the bulk gas, when it is evacuated, we use the equation called VdP by dt, that is the volume of the chamber, pressure fall rate, is compensated by the pumping capacity at that average pressure multiplied by the effective pumping speed, S into P. Okay, that S is to be taken as the pumping speed available at the vessel, not the vacuum pump manufacturer's speed. This is called design. Okay, so once you know the things, then you can easily calculate. These equations are simply mathematical simplifications of that. In fact, I was not supposed to teach these mathematical things because I was told to take 1.5 hour design of it. So design contains several other things, but this is a pump down calculations, etc. This is not design, but it is related to design. So you go through these things. What goes out of the chamber is VdP by dt. What comes into the pump is S into P. So these two, when you equate it, when you solve the equation, is a differential equation, you will get the left side time that is equal to the volume of the chamber V by the effective pumping speed into log of from any P initial to P final. That P initial can be 760 to 740, let us say. That ln P naught by PA, you have to use 760 by 740. That 750 tar, you have to take the pumping speed of the manufacturer. And at that, you have to take the viscosity and calculate the conductance. So use this and find out the effective pumping speed. So if you do all that, you put that as the S. And the pressures of your interest, 760 to 740, you put it in the ln within the parentheses, brackets. Now you calculate the time required from the 760 to 740. Now 740 to 720, again you repeat the equation. Nowadays, programs are available. You can make your own program and you can use your logics also. And you can do analytical way or you can do your numerical way also. You can do all these calculations. I will not go into the detail more than this. but because of lack of time, because I need to cover many other things. If time is there, later we'll come back to this. Next slide. So this is a simple example. You read this 1 minute and you also go through the figures and get the equation, whatever I have done, because you are all teachers, you can easily understand what it's all about. That chamber is there and pump is there. One big blue color is chamber, other thing is pump. Okay. And it is starting from 1000 millibar. It has to go up to 1 millibar. That is our aim. Rotary pump is starting at 1000 millibar. How much time it will take? It and the chamber volume is 50 liters. Okay. And pumping speed is also given as a particular pumping speed, 2 liters per second. Normally rotary pumps are per minute, so 120 liters per minute. So pumping speed is given. And I told you pumping speed itself is a function of pressure. That will complicate the equations. I'm not putting all that in your mind right now, because then you'll have to do finite element method. You take it as a falling curve can be taken as a step type of functions, and then take that average of that particular P and P initial to P final. All that complications you can easily follow later. In fact, we don't do all these things. Just do some rough calculations. Okay. So please look at this equation. What is given here? Volume of the chamber is given. Pumping speed of the pump is given. And the requirement is from 1000 millibar, that is atmosphere, you have to go up to 10 millibar. Quite a reasonable thing, because 1000 to 10 millibar, already 99.9% of the bulk gas has been removed. Afterwards, these high vacuum pumps, turbomolecular pumps, they are not removing the chamber gas. They are mostly removing the gases coming into the chamber by evaporation, by degassing, by leaking. They are much more compared to the remaining micrograms of gas which were there in the beginning in the chamber. These are milligrams. So high vacuum pumps are not pumping the chamber gas. High vacuum pumps are pumping parasitic gas loads and process loads. Whereas the normal vacuum pump, which is 99.9% of the gas is removed at that time, and costly, it's not costly at all. But this parasitic loads that is to be removed from 1 tar to 10 power minus 10 tar, it is only in macrograms and nanograms, but all the applications are there. Up to 99 runs, nobody cares. Last one run is very important. Same thing in vacuum technology. 99.9% of the gas has been removed by that 20,000 rupee rotary pump. And within 10 minutes, that 0.1% gas takes from 1 millibar to 10 power minus 10 millibar, and that will take more than 20 hours. This takes 10 minutes, 99.9%. That will take 20 hours. And this pump is 20,000, that pump is 20 lakhs. And this, if you don't want high vacuum, the chambers can be rough. The chambers are very simple, iron or stainless steel. But in high vacuum, if you want, you need to have gold gaskets that. So cost of the chamber goes down 100 times. Cost of the pumps go up 100 times. And time also goes 100 times. And component style also goes. All that is removed only 0.1%. Otherwise, we will not get space technology, we will not get nuclear technology, metallurgy, we will not have any viable electronic technology, no electronics. If you are removing 99.9% air from a chamber, you cannot start semiconductor at all. There is no laptop, there is no iPad, there is no cell phone. If only we can remove 99.9%. It is only the 0.1% that makes a lot. But right now, the example that I have given is how do you remove that 99% to get a feel of mathematics. Now, with these ideas of 2 liters per second pumping speed, which we assume constant, it may fall, but we assume constant, because up to 10 tar, most of the pumps maintain. Rotary pump pumping speed starts falling below 10 tar. Okay. So look at the question, look at the diagrams, look at the calculation, and get the answer. Just I will give you 2 minutes time. This is very important for the system design. That's why. Please go through it. I'll come back after 2 minutes. Okay, assuming you have gone through it. What is it in this example? It is taking 115 seconds. That means 2 minutes for a chamber of 50 liters going from 1000 millibar to 10 millibar. This much design system, you should do it. If it may take, instead of 120 seconds, it may take 200 seconds, but it will not take 20,000 seconds. So when you say 2 minutes, it will take from the calculations, but it is taking 200 minutes. Something wrong with your either calculation, or chamber is open, or valve is not open, or gauge is not working. See, what is problem in a vacuum? Vacuum is not coming. So you should ask yourself or ask your student, if expected vacuum is not coming in expected time, what can be the reason? Huge amount of water is there at 10 tar, it is evaporating. Earlier it was not evaporating. It was only that ambient gas I am removing. But now suddenly huge vapor source, steam is coming. Because boiling point is at 2010 tar is below room temperature. Room temperature is a furnace for it. It will evaporate till that, and water will take lot of time to evaporate. 1 cc of water, if it evaporates, it produces 1000 cc of vapor at atmospheric pressure. That 1000 cc will become 1 million liters at 1 tar, because but 1 tar equivalent liter is rarefied. So all these concepts, last class also I told, but it will not be so fast. You cannot get that. You have to read again and again. Then only you get a feel of all these things. But right now, if we are 120 second is not happening, you should doubt whether valve is opened at all. Sometimes I have seen students are saying, sir, pump is not working. I'm not getting vacuum. Then what you should do, you should hear the sound. Initially, hissing sound, because huge amount of gas is going through the rotary pump. Some cushioning will be there, so hissing sound will be little soft. After some time, very small molecules are coming. That time the metallic sound will come. So if it is coming, then pump is running, and you can put your hand slowly and just see whether it is running. These are the tricks. Okay, and if it is getting very hot or not, you should check. Then unnecessarily it is compressing a leaky gas. That means your chamber, some door is open. That may be a reason. Or the interconnecting pipe is not opened, valve is not open, or the pipe is maybe 10-meter long. So conductance is so poor, you are having 120 liters per minute, but actually 0.1 liter per minute is the pumping speed available at the site. That may be the reason. So you will have to start thinking about all these things. In last life, sometimes common sense you have to use. Gauge may not be working. Actually, vacuum is coming, but gauge is not working. Okay, so all these things is a part of system design. Next slide. Now, when you go to the high vacuum below 1 tar, pump may be running, system is there, you have to do your operation. Your boss has told, go to the oxidation, go to the lithography, so many things. You can't start even beginning because you got only 1 tar, 0.1 tar with rotary. Now turbo pump is on. It is taking, you have calculated 1 hour, but it is taking 100 hours. Vacuum, it's not coming. That is because the molecules from the chamber do not know that there is a pump. There is no drag because mean free path is much longer. I explained in the last class. And the chamber diameter, the pipe diameter is very small. Chamber is too big. It has to go through that port where the pipe is connected, and other side pump is there. So chamber is this side. It has to enter. Earlier, from 1000 millibar to 1 millibar, it enters like a streamlined flow because of viscous drag. Now there is no drag. Each molecule is independent. It will go every direction. It might come. So there is a statistical calculation has to be done for measuring the conductance formula in the molecular flow. So the pumps are also called molecular pumps, turbo molecular pumps. It is not called rotary drag pumps, etc. So as the pressure is going down, flow is also slowly shifting from the viscous flow to the molecular flow. So the conductances are very small, and it's constant conductance in the molecular flow. Whereas in the viscous flow, it's a function of pressure. Higher the pressure, the drag will be more, etc. But once you cross, lambda is much, much more than the diameter of the connecting pipe. Whether it is -3 or -4, conductance will be same. Okay. So 1 lakh rupee minus 1 paisa or 3 paisa, it doesn't matter like that. So when in the molecular flow, we need to worry about leaks much more. Because even if a small leak from the atmosphere enters into 10 power minus 6 star, initially it may be 1 cc of gas in the flow meter in the atmosphere side. But that 1 cc of gas, if it is leaking inside, it will be 1 billion liter, billion cc, because it's the rarefied atmosphere. So that you have to consider. Now, this is a part of the system design. You should know these things. So just go through this half a minute. This is the molecular flow, which is happening below 1 tar. Just go through it half a minute. Okay. Assuming you have gone through, you can go to the next slide. If you don't understand, you can raise the hand right now. And these are the calculations which you have to use to know the conductance of the pipe that is existing between the chamber and the pump. I need not discuss all these calculations. You just have to, you come to the last calculation, right side, that is 12.1 d cube by L by 1 plus 4d by 3L. This equation you should remember. Okay. If it is a valve, you should know it's only an aperture. A valve, actually aperture is what? Opening, zero thickness, that is called aperture. That also has got conductance, because chance of going through the aperture may or may not be. Whenever there are chances, there is a probability. When the probabilities are there, that's called aperture conductance. Because in turbomolecular pump, when it is pumping the chamber, we are already in -2 tar created by earlier pre-evacuation by the rotary pump. Now main free path is much more compared to the dimensions of the chamber as well as the pipe. So some molecules will come. It has to flow through. First, it has to enter into the orifice of the pipe. The pipe is nothing but an orifice followed by pipe. That orifice is called aperture. So you have to use, if the pipe is very short, then you have to use the left side formula. But most of the time we don't worry about it. The right side, because we will definitely connect fairly good amount of long pipes. We cannot make diameter very big and length very small. Then that becomes another chamber to be evacuated. It's not a pipe. Okay. After all, your chamber is also a pipe welded, etc. It is like 1 meter dia, 3 meter dia. If the connecting pipe is also 1 meter dia, then there is no meaning. So, okay, your volume will increase like anything. Dead volume increasing. Yesterday he was telling the thin film deposition unit time. The volume of the chamber should be as small as possible, so that the amount of costly gases consumption will be less, and the maintenance of vacuum is also very good in deposition units. But when you go to the space simulation chambers, the volumes are like the building size, because entire space shuttle has to be kept in that, and they want to see whether this fellow will degas, not the chamber, because this is going to be there at 24,000 kilometers somewhere in the geostationary orbit. So that vacuum they are simulating here. So for them, very large chambers. You go through the internet, space simulation chamber, you will find your building wherever you are sitting, entire building can be inside. That level of thing. There are thousands of turbomolecular pumps are parallelly connected. Cryo pumps are connected, ultra high vacuum. That is another challenging problem. Just like Your semiconductor is a challenging problem with respect to contamination, with respect to controls and atomic level, dopings, etc. Each has got their own problem of vacuum technology. Without vacuum, that space simulation will not start. This nuclear particle acceleration will not start, because as soon as it gets accelerated by the electric field, it touches by some other molecules, get decelerated. Without acceleration, no fusion, no fusion, nothing. So no nuclear engineering, no semiconductor technology, no space technology, and no metallurgical, advanced metal technology. Only some iron technology will be there. So all the technologies will collapse depending on the vacuum level. They will start opening up to 10, 100 only up to 200 tar. Already you are removed. If you are making 10 tar, you are already 99. See, 100 tar means, sir, 100 millibar, let us say. 1000 millibar is the atmosphere. 90% gas has been removed, but no application excepting train stopping or some vacuum cleaner or something. But below 90 to 99, evaporating water, that is for the Kisan squash, fruit juice manufacturing, or chemical industry where distillation is going on. Some mundane industries have started up to 1 tar. 99.99 is over already. Nothing, no metallurgy. Below 1 to this one, 99.999, if you go, you will start getting metallurgy. 99999, semiconductor. 9999, 5 times space technology, nuclear technology. So it is only a very small amount of further removal that creates all these things. That's why molecular flow conductance plays a very important role. Just like rotary pump, we have seen 120 liters has gone to 1 liter. Similarly, here, turbomolecular pump, they will say, to you purchase 40 lakh pump, it is around 1000 liters per second. You connected it, and by mistake, you made a small pipe, which is a very small in aperture diameter and long in length. Then that 1000 liters per second has gone to 1 liter per second. Then where are you? So the company fellows have sold and gone. And chamber is also very neat. They are also made the chamber from America. It came. And beautiful power supplies, RF, everything imported. Nothing is made in India right now. Neither we make microwave sources, nor we make good RF power supplies, nor we make E-beam material, high quality materials, nor we make walls very high quality, nor we have any measuring equipment very high quality, and low degassing vacuum chambers are not there, and pumps are being manufactured, all imported. So what is this? Now we are going into one by one making these things indigenously. That's why when the technologies are demanding all these other technologies related to semiconductor, that is called ecosystem. Semiconductor ecosystem. You require water, you require pure gases, you require pumping technology, you require very good chamber materials, you require clean rooms. So all these other technologies, which are mostly imported, now you have to worry at molecular level. Okay, so these are the equations you should remember in the system design. So this worry itself is called system design, because you should feel always uneasy. Oh, vacuum may not come. Even if it comes, impurities may be there. And even if impurities are not there, the actual things are not flowing up to the point and dipping. Or it may be overdoped. Then silver is closing, or lithography is not proper. Every step you have to be systematically accurate and repetitive. If first chip is one thing, second chip is somewhat different, then you 100 people purchase same model cell phone, each cell phone will behave in another manner. So reliability is very important. Microelectronic reliability, there is a journal on that. Semiconductor physics people, they put there, because hundreds of cell phones they will try whether all the chips are identical or not. So this is not an easy joke that semiconductor manufacturing will do. Oh, first you have to understand the molecules. You have to understand the boiling points. You have to understand the fluxes. You have to understand the mean free path, vacuums, various costly components. No leak is allowed. Unintentional contamination is totally not allowed. Parts per million impurities. All that who will take care? Vacuum technology takes care. That's why it is the base of the semiconductor manufacturing. Next slide, please. Now, this much introduction we have done for the system design. In fact, today's my topic is only system design. But if I tell directly in showing this as the slide, you feel nice, but you don't understand. Whatever I have told, You put all of them here, that is called system design. Okay. Now there are central point is vacuum system design for different applications. This is a general photo for all. This I have made it for general things because I regularly organize process application courses. I do cryogenics, I do chemical industries, then pharmaceutical industries, nuclear industries, space industries. Your semiconductor is one of the industry. Okay, metallurgical industries. Different people, the way systems are designed in different manner. But one thing common is leak should not be there, degassing should not be there, conductance should be as much as possible, and cost should be minimized, chambers should be tight, leaks should not be there, and seals should not be degassing, and the chamber should be backable. That means you degas it intentionally so that remove all the junk, and then during the actual application you are having a clean atmosphere. Cleanness means vacuum is clean, no doubt, but ultra high vacuum is ultra clean. So now semiconductor is ultra clean. Whereas if you are doing vacuum technology of say or chemical industry, 99.9% removal. That's also not small, but that's enough for them. But you have to do 99.99999. If you do 99.9% removal and do the coating, you will have thin film will be formed, everything will form, semiconductor doping, everything will take place. 99.9% vacuum you have removed, your gases you have removed. But your device will be 10 rupee. It will not be 10,000. I'm telling you. Device will not work at all. It is a junk. This is what you should remember. Pump selection is important. As now you come to the one by one circles. The yellow circle says pump selection. Since you are doing a ultra high vacuum, it should be dry because if pump itself has got a lubrication, because every mechanical or any pump, it should be lubricated. Otherwise, it will be a wear and tear. You purchase 10 crore rupee pumps and after 4 or 5 months, it is gone. You cannot do that. So they are lubricated, but that lubrication oil will evaporate. And in ultra high vacuum, flow is always not from the chamber to the pump. There can be from the pump to the flow because nobody knows. Each molecule is independent. Just like molecule from the chamber goes all the way to the pump, pump oil molecule also will come all the way to this through the same pipe. And they are non-interacting because mean free path is very long, kilometers. They will only hit multiple reflections in the body of that pipe, but they won't hit each other because you're already below 10 power minus 3 tar. Thermal vacuum is up to 10 power minus 3 tar. That is good enough for flask making. And mechanical vacuum is up to 10 tar, 100 tar. 10 tar is the vacuum for evaporating. 1 tar is the vacuum for thermal. 10 power minus 2 tar is very good thermal. After that only semiconductor, ionization, laser beams, space, nuclear, all this. Okay. So that dry pumps have to be there. Dry turbomolecular pumps, dry backing pump. It's not only important that 10 power minus 5 tar very dry turbomolecular pump we are creating, but initially somebody has to evacuate from rotary pump from atmosphere to 10 power minus 2. Who will do that job? That is it. If that is also should be dry pump. If you are to be very good, it is not important which college you have studied in BTech. Right from the history, it is important. Where you studied class 1, where you studied class 10, where you studied JEE, where you did BTech, where you did MTech. Entire history of evacuation is important. Okay. So you right from the beginning, all the pumps should be very dry. They should not have oily. That is the first system design. Then process related issues, safety, water treatment is required sometimes because you cannot pass any water inside. Okay, some like sputtering targets, cooling, etc. There may be micro leaks if it enters, and if it is an impure water, you are in trouble. Corrosion is another problem because impure waters and all they will corrode some of the things. They may not be going, they may be indirect cooling, but the pipe gets corroded. Or corrosion, erosion, these are the problems. Environmental constraints have to be seen. Wherever you are throwing this gas, silane gas in the semiconductor, all the way from the turbo chamber through the pipe, turbo pump, rotary pump, and in between turbo and rotary, there is another pipe that also has got conductance. And then finally it comes to the rotary and get exhausted to the atmosphere. Not allowed. Your next fellow will say, I don't want your silane out. So all these things, how are you going to do that? There will be scrubbing actions at the end of it. You have to wash and to put that exhaust management is very, very important. That is a system design concept. And any circuit, anything that is problem, you have to repair it. That pressure gauge or mass flow controller or electrical heating, voltage, current, and high voltage, magnetic fields, electromagnetic field, that is called instrumentation, containing actuators, controllers, manipulators, leak detectors, residual gas analysis. You may have 10 power minus 7 torr, but there another fellow may be having 10 power minus 6 star. He will get a better semiconductor chip. Why? Because the 10 power minus 6 star is full of inert gas like argon or helium. Your 10 power minus 7 star has got oxygen impurities or some other hydrogen impurity. Namesake molecular density is less, but your chemistry is bad, physics is good. 10 power minus 7 star is definitely a better vacuum compared to 10 power minus 6 star. But from the chemistry point of view, you still have 10 molecules of oxygen or hydrogen. That fellow may be having 100 molecules, but all 100 are inert gas. So nothing will happen to the semiconductor. They will not get doped. So that is called our residual gas analysis. It's not only important to get a good vacuum, you should analyze that residual, whatever is the residue. Okay, that is very important. And leak rate should not be there. You are continuously evacuating 10 power minus 9 tar. Since you are continuously evacuating with huge number of pumps, you are maintaining the vacuum. The moment you isolate the pump, immediately pressure will rise. That means what? There is a leak. So leak is not allowed. So this leak, when it comes, mean free path, when it enters inside the chamber, it is 10 power minus 8 tar equivalent. Molecule outside is atmosphere, but through the leak it came. There is a constriction. It leaked inside. Then it will fall. It will directly go and hit your substrate because it is a straight line path. So instead of you evaporating some copper for the metallization, that oxygen will go and it will be a reactive sputtering. And instead of having a metallic contact, it will be metal oxide contact. So leak rate has to be very less. And sometimes in all these things, you cannot avoid some bit of leaks will be there. So Q is equal to S into P. That left side I have written with the black color. That is the most important box. If you can increase the pumping speed, then for even if Q means all possible leaks are gas loads together. It can be Q1 plus Q2 plus Q3, various loads. Mind you, there is no load of initial existing gas that has been removed up to 99.99 by rotary pump already. This is only process gases that are getting evolved or leaked. That is only it is handling. Okay. This Q is to be equated to pumping speed of the turbo pump multiplied with the vacuum level P that you want. If unavoidable Qs are increasing and P, if you want to be very, very small, then S should be increased like anything. That is the design. It may be overrated design, but your boss says, I don't care. There are some leaks. I don't have time. We have to make it. Then increase the, instead of one turbo molecular pump, come two pumps. Then next day, we have enough time. You can repair it, but I don't want too much of pumps. I want one pump to take rest. Then you have to reduce the Q, unavoidable leaks, etc. Then P can be less. Either you reduce Q or increase the pumping speed because product is conserved. Okay. So chamber design, that chamber should be very leak tight, and wherever it is not as monolithic chambers are made. It is like Ajanta Ellora caves. You don't make one flange, one welding, one pipe like that. You take a ingot and scoop out material, make the chamber. Have you seen Ajanta Ellora? You will see the entrance gate as well as the corridors as well as pillars. Everything is out of one stone. So that is called monolithic chambers now. They will not dig as much. So that sort of chambers are being used. Okay, that is chamber design. All the materials that you are going inside for manipulation of the substrate from this side to that side, holder of that, heater of that, that is made out of some materials, chromal, nickel, cement, all that. They should be compatible to the vacuum system. And if it is a sealed device like X-ray tube, once evacuate, no more pump is there. It is evacuated and sealed. Leak rate should be very, very small for that. because it has to stand 20 years, 10 power minus 8 torque. There will be local small sitting adsorption pump layer that's called gettering pump. I think pumpman, the pumping, there must be somebody who is going to explain vacuum pumps, etc. They will explain ion pump, etc. But right now, you have to take care from the system design, selection of the pump, instrumentation, the valves and components, safety, and the ecosystem like water treatment and pure gases. Even if you have 99.99% gas and you are producing 10 power minus 10 tar and you are letting that gas, it is of no use. If the gas purity contains third 9 is the impurity, then what is the point in evacuating to 10 power minus 9 tar? Just like ultra high vacuum is equivalent to 99.99999% pure gas. So that's why the gases involved in semiconductor, 99% of argon is only 1,000 rupees. 99.99 is 10,000 rupees. If you want 5 nines, it will be 10 lakh rupees. So just like here, the chambers are normal chambers, only stainless steel chamber, burden like our vessel, it will only be 2,000 rupees. But if it is ultra high vacuum, the thickness has to be chosen like that, the permeation need not be there. The thickness has to be chosen, it will not buckle under ultra high vacuum. But of course, buckling, once you are testing the chamber up to 1 tar, it will not buckle up to 10 power minus 10 tar, because buckling is the mechanical pressure. So system design fellows have to calculate the thickness of that chamber. If you have made a mistake, as soon as pump is on, the chamber will collapse. Okay, just like when you are taking a plastic thing and evacuate, it will collapse. So that should not happen. But that doesn't mean that you increase the thickness unnecessarily. It will be very costly. There is an optimum thickness beyond which, even if you increase, it is of no use. If you are interested in minus 7 tar. But if you are wanted to go 10 power minus 10 tar, even though mechanically it is of no use, if thickness is more, permeation will be less, diffusion will be less. So you have to take all the concepts into parallelly to make the design of that's called chamber design. Okay, instrumentation, sealed or non-sealed, or continuously running with and without vapor, depending on that pump selection and wall selections. Each wall itself should be UHV compatible. After all, it is connecting a high vacuum chamber to a high vacuum pump. So if the valve is leaking, you are in trouble. So these are the various things. With this idea, you go through this slide for at least 1.5 to 2 minutes. I'll come back. Just go through this slide, all the circles. Okay, I have explained, but you should go through it because this is the most important slide. This is the system design. Afterwards, even if you are leaving the class, nothing will happen. Hope you have understood some of the system design concepts. These are the various sub boxes and they are all linked to the system design. You go through it later, and if you don't understand, it's very easy for me to talk to or to your company, college people or company people separately also. That's not a problem. Because basically, you don't have to make your own pumps. So you don't have to worry even if you are not able to understand rotary pump operation or turbo pump, because you are not going to make. And you are not going to make chambers. You are not making gauges. You are not making instruments. But what you are making, connecting them optimally, system design, that is very important. Even if you are not understanding the other aspects of vacuum technology, but if design aspect is not there properly, even this does not matter. If you think that for 1,000 rupees you have spent 1 lakh rupee and it does not matter, then it's okay. But you could have done it 1,000 rupee, maximum 4,000 rupees. But unnecessarily, because you don't know the system design properly, you have unnecessarily overrated and everything. You have spent a lot of much more money. System design is important for varieties of reasons. One is quality of the product. The other is cost effectiveness. The third thing is reliability and sustainability. Okay, these things. Next slide, please. This, of course, uh, you can go through at your leisure because this is only a curve showing a pressure versus time curve. Initially, the volumetric gas that is within the volume was. Afterwards, surface gases. Afterwards, diffusing from the outside through the body of the chamber. Then finally, it saturates at permeation. That load you cannot avoid because from the walls outside, like 10 days before it has entered the stainless steel, and now it is coming out of the inner side of it. That will be continuously fluxual behavior. That's called permeation. So these are explained in this slide showing the pump down time related to the vacuum system design. So if you are interested up to 10 tar, etc., only volumetric gas. But if you are going up to 10 power minus 5 tar, you need to worry about surface gases, liquids, evaporate. By chance, you have put a sweat there or some other fluid is there, which is unwanted, but it is now leaking. Initially, it was not known to me. So like that. And if you want to go to still higher vacuum, you have to worry about the way you are putting the thickness of it, the seals, instead of having rubbers or neoprene gaskets, you have to have a metal gasket. Since you have put a metal gasket, the flanges should be tightened so high so that the metal flows like a gasket. So that is called yield strength of that solid material, because of copper, stainless steel, they have got yield strength. So between two stainless steel flanges, there will be one flat, one sharp edge will be there that will make a dent on that, because high stress when you are applying, instead of having a clamping of the flanges, you need to make the tightening of bolt and nut type thing. So if you do all that, a typical ultra high vacuum system looks much more stylish compared to a vacuum system. But it's not always required. So sometimes over enthusiastically, you spend much more than what is required because you are not good at system design. And your system is only 10 power minus 6 tar. You don't require minus 9 tar. You are unnecessarily putting some copper gaskets. And a copper gasket, one time you can use. The second time, every time you open and see your product, again you have to put fresh gasket. Whereas if it is a normal gaskets, you can repeatedly use it. So all these things play an important role. Next slide, please. Same thing I have continued because gaskets, and it's in English only, you can read through it. How the pump down timings are related to the selection of the material, and how can you predict the pressure, time, etc. And why should you predict? Because you want to make 1 lakh chips, 1 crore chips within 10 days. Demand, like Corona time. If only not much, only hundreds of people are sick, then our industries could have done. But why you require so many cylinders of gas? Then you are in trouble. Speed matters there. How, when you are making the speed as a criteria, then system design is important. If speed is not an important thing, it doesn't matter. After 5 days also I will get it. Then it's okay. Okay. So what you can afford to do, affordable leaks are unaffordable, you cannot afford at all. So these are the decisions have to be taken. That's called management of the system design. Okay. Next slide. So this is same, Q is equal to S into P. This is the fundamental thing. For a given load, that load can be process load, that load can be unavoidable leaks, that load can be some other leaks, all are evaporation, all these things inside coming from the surfaces, they are called outgassing. Coming from the outer, they are called leaks. Coming from the actual melting and evaporating, that's called process. There are process loads, outgassing loads, and leak loads. All these three are forming disturbance to the clean ambience, and that residual gas that is formed out of these things, while it is continuously evolving, continuously pump is removing. But there is an equilibrium. That equilibrium is called residual gas. That residual gas, you have to analyze it using mass spectrometers. If you do that, then you will be able to understand, oh, even if it is bad, but that bad thing is only argon. So go ahead, go to the lithography, go to the etching, doesn't matter, because this argon is not going to make a make. But if that fellow is some another p-type impurity and you are actually depositing n-type and all, you are in trouble. So, and your pumping is only that much available pumping speed is there, but you don't have money to purchase the additional pump. Then you have to be minimize all the leaks properly. And because a small salary, but still you have to eat, then you have to make a lot of savings everywhere, wherever you have to. You should not unnecessarily spend. So you have to be very careful. Same thing in vacuum technology. If you are having only one pump, and then the connecting pumps should have very good conductance. But at the same time, if you in the process of making, if this cost of the pipe goes up, then again it's not allowed. So you have to use continuously in a reiterative manner the design estimation of it. So that is where the intelligence lies, and sometimes artificial intelligence. Okay. Okay. Next slide. So finally, what are the problems in a system? That's a part of the system design. If you want to become great, first you should know your weaknesses, your enemies, your health, your background, everything. Then only your effort and your ongoing training, all these things matter a lot. So same thing what are the problems in a vacuum system? What is the problem in vacuum system? Vacuum is not coming. That it can be backstreaming from the pump because it has got some oil vapors in the lubrication. That is number one. Number two is permeation. The body is made out of a useless stainless steel which you have purchased from local market. It is not buckling because it is thick enough mechanically, but it is having blowholes. So a lot of gas is permeating. Or diffusion, initially you have put some here and there some nuts. If that nuts there is some trapped air is there, that will slowly diffuse out from the body itself contains in the steel plant some occluded. After all, steel sheets are made and bent through the various assemblies in the hot rolling. So some gases might have been dissolved in that stainless steel. They will now come as a diffuse out into the vacuum because low pressure. That is called diffusion impurities. Diffusion is a phenomena for p-type impurities. That is a process-related diffusion. This is a diffusion related from the chamber wall into the chamber. This is a bad diffusion. Desorption, whatever is the junk, some small amount of smell may be there, that normally will not degas up to 10 tar. But now it will degas because the vacuum level, the pressure existing is less than the saturated vapor pressure of that particular semi-liquid phase. When it is getting, when its out pressure is less than my saturated vapor pressure, I will saturate that so that I will dissolve. That's the desorption. And if I am a liquid, I will evaporate. Desorption is a surface phenomena. Vaporization is a bulk phenomena of a liquid bulk of liquid, drop of liquid. Then it will evaporate. Internal leaks, external leaks. And the chambers that you are using. You see, aluminum is a better chamber than the stainless steel, but most of the time we use. So bottom figure shows as a function of time, if the chamber is evacuated, the inside lining gets purified. Okay, but initially stainless steel also degases. That will also give gases. But as a function of time, it will come down. And if you see for the same time, aluminum is better than stainless steel. But you cannot use aluminum chambers because aluminum is not weldable. That's what most of the other fellows will do. But semiconductor fellows are intelligent. What they are doing is aluminum is easily machinable, and this fellow is telling that outgassing is less. So and lightweight. So immediately what they will do, he will take a very pure aluminum bulk and scoop out, make a film, make a chamber, and another scoop out, make a small flange. All it is made out of a monolithic, just like you make a curved structure of a guard out of that. So coupling, everything is made out of a single body. That's called monolithic chambers. So, but it's not weldable because aluminum, if you want to weld, you are forming Al2O3 at that. Alumina is a ceramic. That's the reason aluminum is not weldable. Whereas stainless steel is well. And aluminum is not weldable for another reason. It's a good thermal conductor. Whatever thermal energy you are giving, it will be conducted away very fast to the remaining of the aluminum. So these are all very important. There is a lot of metallurgical research going on in the material science and metals department. Advanced materials. There, how do you weld? When you are welding aluminum, it will form like a lot of lump, etc. So how do we avoid that? Laser beam weldings and varieties of E-beam weldings, they are all coming. This is a part of it because the need for all this high technology came as an ecosystem for the vacuum system. And since the vacuum system is the compulsory thing ensemble for the semiconductor. So each is now trying to attract the other technologies. So a whole lot of ecosystem is involved through the vacuum technology applied to the semiconductor manufacturing. So these are the sources of gases. You need to do that. So baking is one thing where you can remove all this diffusion, distortion, and making the chamber very high quality stainless steel. Roll that sheet again and again in between the rollers, so it becomes dense steel, and then make a chamber by welding it. Then that chamber will behave better. And see to that all the walls evacuated. When you are opening it, you don't open suddenly to air. You open it to a dry nitrogen or dry air, so that the first layer, first film that is formed, that virgin film, whenever vacuum chamber is vented, because you have to open something and really take that chip out. So though there are manipulators from high vacuum to the medium vacuum, then close it. From that medium vacuum, you open it. That's called load lock chamber. So many system design aspects are coming into this picture. But it is up to you whether you are making a telephone chip, then you need not worry. But whether you are making a laptop chip, then it is you need to worry. But if you are making a supercomputer chip, you need to worry all the more, because reliability is much more. Quantum computer, all the more. So you cannot make 1 in 10 lakh also error. So these are the things from that side. From this side, the vacuum fellows have to worry. On this side, contamination, air, materials, metallurgy, all these things. On the other side, chip design, this, that's VLSI, they will tell something. But in between, you are in, as a design engineer, vacuum system design engineer. If you are not careful, they will not be able to do their job. That way, you become very important. So you have to convince that system design and making cost-effective system design. Even you can make a very good system design, but it's not cost-effective. But if you spend 20 lakh rupees in a party, anyway it will be good because a lot of wastage will be there. But not that. Optimization is very important. Next slide, please. So with all these designs, fabrication you have to do. You have to fabricate the chambers. You have to fabricate the pipes, etc. Fabrication of the chambers, thickness is very important because vacuum it will collapse. You have to follow the ASME section 8 code, so the structural collapsing will not be there. So that thickness calculations I have given separately. It is very easy. Section 8 is there. That is external pressure equivalent to that, because vacuum is external pressure vessel basically. So you can go through it. It is a typical mechanical problem which you can go through without any training. Okay. I think time is also a gap, so I cannot go through the component level, how to do the system design. But if you go through, read it, degassing should be minimized. For that, you will have to put high vacuum flanges are always sealed with metal gaskets. And you need to, anyway, it is slowly degassing, you are never getting into trouble. So better degas it much more before the process is started. That's called degassing. Outgas is, it is coming out. Degas means you intentionally degas it. Outgas is naturally fellow is coming. Slowly it is coming dig out. It is so nagging, unless that the outgassing is completed, you cannot start your process. Now you bake the chamber so that you outgas much more. That means intentionally making them outgas more so that all the gases are exhausted. Afterwards, no more gases on the surfaces. Then you can at least do it. It is like homeopathy. You increase the temperature by putting antibiotic. Then that will fellow creates much more antibiotics naturally. Afterwards, disease will come down. Initially, fever increases. So same thing here also. So if degassing is an intentional increased outgassing, but during that time, your process steps will be off. You should say stop oxidation, stop impregnation, stop doping, everything. So actual things are all waiting. When the atmosphere is clean, only it will come. So these fabrication methods, including cleaning of it, what type of cleanants you have to use for the fab, for the actual whatever is exposed to the vacuum, including the wafer on which you are forming, including the walls, including the manipulators, including the heating elements, walls, pins, feed throughs, everything has to be degassable Everything has to be bakeable. Everything should be leak tight. Everything should be fabricated. If there is electrical feed through, you have to fabricate it through a metal flange because it has to enter current from outside to the inside. So there must be flange, then insulator, ceramic, and then metal. Otherwise, metal electrode will short circuit with the body. So that is called metal to ceramic sealing. And afterwards, ceramic to the lead sealing. That lead can be an ion pump or an electron beam deposition or ion beam depositions. All of them electrical things. You have from the outside the vacuum chamber, you have to pass currents, voltages inside that. How do you do that? Electrodes. But the electrodes are crossing the vacuum chamber. So you have to take all this account while in the fabrication. So mechanical engineering aspect, ASME, electrical things, you have to have ceramics and brazings metallurgically, sealings polymer wise, and calculations of pumping speed by reducing all these things, fluid mechanics and molecular dynamics, Monte Carlo techniques, and outgassing with residual gas analysis and mass spectrometry detectors using all that costly instruments which are imported. You can make it. If you make any one of these things, you will have a very good startup business. I'm telling you. So there are more than 30, 40 items are there. All 30 are imported now. Even if you make one, you can be billionaire. I'm telling you. So with this, let us now go to the next slide. Now, a typical vacuum system will look like that. If you can amplify that left side fellow, uh, I don't know how you do it, but because I don't have control. Yeah, still. See, there are walls, flanges, gaskets, walls, everything you have to do. That's it, enough. So one thing is vacuum compatible manipulator. This has got x-axis, y-axis, z-axis. Entire this fellow will be inside that vacuum chamber. And if you see from front side, there is a glass window. So glass has to be vacuum tight, and there should be O-rings on that, and it should be vacuum. There are flanges with bolt and nut. Those are con-flat flanges. They will be sealed by the metal gaskets. There are small KF couplings. They are with the O-rings. When to use O-ring, when to use flexible bellows, when to use what type of walls. So many components and central chamber. One is high vacuum chamber, one is a load lock chamber. The wafer will come first somewhere, get its own clean, then it enter into the next higher level. Just like before you enter into a temple, first you enter into one mandap, then wash your hands, then go to the next. This is a semi-vacuum, then high vacuum, then ultra-high vacuum. Between that, there are walls. How this is manipulation is going on. And these robot arms, they should be vacuum compatible. But you are operating them from outside. How those seals are made. It's a big business. And I can easily explain one by one all these things. And the budget is very important. Now you reduce it again. Slightly reduce it so that you can read that. So vacuum component design is very important, whether it is chambers or gauges. The gauge should be compatible. The normal gauges that you will purchase from the local market, that gauge pipe has got some araldite junctions, etc. pins. If you put that ultra high vacuum, the gauge, near the gauge, there is a air leaking. So chamber may be good, but local vacuum is spoiled. Gauge is showing -1 torr. Actually, it may be -3 torr. And it is leaking into the chamber also. Gauge is spoiling the chamber. Okay, you have to do all these precautions when you go for the system design. These precautionary measures, what seals you are using, what flanges you are using, what pipes you are using, how do you maximize the conductance, what is the thickness of the calculation, so that with minimum material cost, you are making a very good quality. Polishing, because if you do not polish the chamber, surface area is much more. Distant hills are very smooth. Like that, the surface area is nothing but 2 pi RH if you take a cylinder. That's what you are thinking. 1 meter dia, roughly this 2 meter, it may be roughly around 3 square meter. That's what you are thinking. But atoms are seeing 3000 square meter because it has got roughness of micro. So unless you polish submicro, the surface area, that is apparent surface area, that is 2 pi RH, when you see in that body here. So for example, here I have square room, 6 squares are there, 4 side and this. So it is only 6 L square. L square is each. That is my surface area. No, but it is a rough thing. As I enter into the atomic level, if atoms are moving, if I am moving with my hand, I will see 6 L square. But otherwise, if atoms are moving on to the cements, etc., it will take 6,000 L square. 1,000 times surface area is increased. That's also a system design. The polishing, making, when you are welding, you are unnecessarily creating a leak sometimes. Originally perfect stainless steel, during welding, you are not proper welder, it has reduced the chromium content of the material, then it is getting rusted after 1 year. So that chamber, you have purchased it for 20 lakhs, after 1 year it is gone. But if you can take care, it will stand for 10 years. Okay. So next slide, please. So these are monolithic chambers. Central chamber, each sub-chambers have got their own pumps, pump, chamber, central chamber. Then between there are square-looking walls. So these walls, one is a load lock. Your wafer, silicon wafer will come to the first chamber, left side, towards my side, it is there. It enters there. At that time, that wall is closed. The central chamber, transfer chamber is isolated. After that, we evacuate, seal, clean something. Then and make it enter into the next chamber. That time this should be isolated. Then it goes to the process chamber and again comes back. Then it goes to the analytical chamber, again comes back. While one valve is opening that chamber to the central chamber, the remaining valves have to be closed. A sequence of operation has to be done, computer controlled. This is all a part of system design. When you are load lock chamber means the first chamber, you lock it from the rest of the high vacuum chambers and you put your wafer, load it, lock it, evacuate it, and then from this poor vacuum, open that valve so that it will take 10 minutes to spoil that vacuum. If it is atmosphere, directly you cannot enter into high vacuum. So this vacuum, by the time it spoils, already vapor is transferred, valve is closed. So how much time it is taking for it to contaminate one vacuum chamber to the other chamber? This is also system design. It depends on the degassing. This can be calculated from the surfaces, surface areas, and the say Monte Carlo techniques. How much is the molecular density at this pressure, that pressure? And if that pump is not good, or central pump should be much bigger, larger volume, more setup. But even if it is a larger volume, if you don't mind waiting for 1 or 2 days, then it can be single pump because it is leak tight. But even if it is a single tight pump, and even if you can afford to wait, but if there is a leak, you will never get the proper vacuum where you can start even. So it is a give and take, lot of things have to be done. This is one load lock chambers, and under vacuum, how do you intercouple these gases with various, depending on the vacuum level, the style of the operation, the style of the valves, style of the selection of the pumps, and the polishing of it, and the manipulation of it, and the gaskets that you are using, that changes. That is a very important. Material selection is a part of the vacuum system design. Next slide, please. So this is the last slide. How much time I have by any chance? Because next speaker may be waiting.
Yeah, sir. We have you can take your time, sir. Maybe 5 to 10 minutes more.
Okay, because
Yeah.
I can keep on talking, but that's of no use. So
No, no. It is
next
so
maybe we can give
informative
more
session.
time and yeah.
Yeah.
So modern, this you can read it. Modern semiconductor chip manufacturing involves several sophisticated clean processes because your silicon wafer is ultra high clean, but it is connected from a box. That box is also evacuated. Just it is clapped. That time load locked. Then it goes to this. If you see the left side from the central chamber, there are 6 things. This we have seen in the first class also. CVD, somebody is going to explain. PVD, somebody is going to explain. Etching, cleaning, ion implantation, planarization, that is polishing, and the pump diffusion. There's a phenomena for the doping. All of them are connected by double arrows to the central chamber, which is a lithographic and masking type of chamber, because layer by layers you have to deposit, etch, oxidize, dope. Finally, when all the things are over, test it whether it is behaving like a CMOS, whether two FETs, N-type FET or P-type FET, they are connected properly channel, and it is connected to the diodes, transistors, capacitors. There is no place for it to put a capacitor. You have to have a vertical capacitor. And how do you connect these things? There's a whole lot of work. When you take a capacitor, these capacitors are not like a small capacitors like these boxes are. These are not the capacitor. This is a micron level because capacitance is epsilon naught A by D. So if you can reduce the gap between the things D, you can increase the capacitance. Or else you can increase the epsilon. That's why special dielectrics are now being priced. Originally, 10 years back, you are only having 20,000 to 10,000 components one square inch. So even if you can afford to have a little bigger capacitor. So in normal paper type, normal oxidation is enough. Oxide layer itself is acting like a silicon dioxide is acting like dielectric. But now it's no more because every component, the active components like diodes, transistors, passive components like capacitors and resistors. Resistors are also important. If you don't have CR circuit, you will not have timer. You will not have floppy flip-flops. You will not have switching devices. Switching devices, flip-flops, transistors, amplifiers, diodes, rectifiers, and CR circuits, and ultra varieties of components together forming a CMOSs. Several such CMOSs are interconnected, and capacitors are, if necessary, laid on the second layer, third layer. Several layers are metallized. All that will be one die. Several such dies are there on a single wafer, and you have to cut these things with a laser cutting very carefully. Things have to be done under vacuum. Before that, pre-checking has to be done. Till now, we have not done metallization. Then you'll have to metal contact right from the bottommost. You have to have some holes. Through that, it has to come and metallization. And at the end, you have to put it between the two plastic things. And then we'll have to bring out minimum number of legs to bring it to the motherboard so that 1, 3 added for first second, 1, 5 is connected second. That's called multiplexer. That fab design has to be made with minimum number of external contacts, maximum number of internal contacts. How do you make as a time and space domain? This is a design by itself. If you do all that, chip manufacturing is happening. And for that, the starting point is to get 10⁻⁷ TAR. Otherwise, you will get, instead of an IC chip, you will get a potato chip. I'm telling you. Because the quality of the chip matters because you are doping parts per million. First of all, that million fellow has to be pure silicon. Then intentionally you are oxidizing. Natural oxidation should be minimum. Then you are opening lithography in the nano scale. Gone are those days photolithography, electron lithography, all are gone. Now EUV, extremely ultraviolet lithography. That setup itself is 100 crore rupees. Okay. So, but system design ke liye you can do some lower level things within the laboratory. You can certainly do. When you do all proper walls, because wall simply connecting a wall in the water pipe, that's also required. But these walls are high vacuum compatible walls. The chambers are high vacuum compatible. The whatever processes that are going on, all those interconnecting links have to be properly conducted. And the surface smoothness of the chambers are very important. And whatever is there inside the chamber, manipulator, because after all you have to connect this fellow to that fellow also should be polished properly. If you do all that, then if your right side you come, the vacuum related equipment and accessories are properly chosen, properly made. Then only the deposition, the top line, second line you see, the processes include deposition, etching, doping, lithography, wafer handling. Everything is facilitated by vacuum and ultra high vacuum. That requires a careful planning of pumps, chambers, walls, components, and feed-throughs, and manipulators, and decision-making, electro-pneumatic controls, etc. When you do all that, the circles are properly chosen, timings are made, then only from the sand you can make chip. Okay, and if it is a very small integrated, then it's called IC chip. When you are metallizing properly, when you are putting in a motherboard, then the remaining motherboard, which is 100 times bigger than this, that is only 1,000 rupee. This chip is 10,000 rupee. Okay. Then if you put, this is all still not the, I have not talked about semiconductor thing with respect to display. I am only talking about XY plane of the computer. YZ plane is LEDs, LCDs. That is also chip. That is also a sort of semiconductor related. If you do not have display, what will you do with this IC chip, which is computing very nicely? That you have to see. So display technology also requires background, lots of logical circuits which are made out of semiconductor. So that further photonic things, then you will have to do the that is a different game. That is light sensitive. They are different. Their photons come, not just electrons. So if you do all that, and if you do this XY plane semiconductor and YZ plane control semiconductor, followed by optoelectronics and very nice looking frame, then you will have mobile phone, then you will have a laptop, then you will have TV. So the story is the system design is so important for cost effective things, because you have to make finally a cell phone costing 1 lakh rupee. Nobody will purchase. You have to make it 2,000 rupees. Okay. So vacuum technology plays an important role. You have seen now come to the fourth quarter, right? Bottom right side. You look at that. Vacuum technology is the basis for semiconductor IC chip manufacturing. And that is the basis of three major components where all the children, adults, old people, everybody is using these three. That is laptop, cell phone, and TV. If these three things, if you don't want, only for defense people semiconductor or for any war, then you can save a lot of money. But without these three, we cannot live. Okay, we can live without any other thing, but not without these three. Okay, that's why semiconductor chip IC manufacturing is solid state electronics. It's not wall based electronics. It contains ceramics, it contains metals, it contains polymers, it contains uh, varieties of new materials even. Okay, semiconductors, dielectrics, insulators. Sometimes insulators are required, and all insulators are not dielectrics, but all dielectrics are insulators. So you should require a lot of fundamental semiconductor physics, semiconductor design. When you are making 2, 3 designs, then mathematics will work. But when you are making lakhs of devices, how they are going to behave? Then fab design has to be there. 50% of the software people have to be incorporated to make the system design. Another 20-30% advanced materials with proper vacuum pumps, system design, and chamber. Another 20-30% semiconductor materials properly controlling, etc. Then packaging, then finally getting and the use. So this is what I would like to say. The first lecture I have given some basic concepts related to vacuum. Now I am giving system design. These three things, if you are attaching with the other lectures where you know some pumps, some materials, some gauges, some equipment, some design, and some processes, depositions, etching, thin films, all that, then you are in a position to understand an introduction to manufacturing only. Just by taking this course, I'm sure they have done very nice planning of linking vacuum, material science, metallurgy, controls and design, and finally making you. But after you go back after these 6 days, you start reading, and even if you make one thing concentrated, you can get a lot of projects. Okay. Thank you very much. Next slide, please. Yeah, this slide clearly, this I need not explain. Now, so much money is available. This is a old slide. Now, a lot more money is coming. So, totally 1 lakh crores is earmarked by Indian Semiconductor Mission Program. And initially, they gave it to a lot of companies. Then they will give it to this. In fact, because of this importance, part of this money is given to this the university. We also get such things for organizing courses. So they are doing a lot of good job in this college. And I'm sure as time passes, with their knowledge of electronics, microelectronics, and very good material science, very high quality polishing, very high quality design, they will be in a position to make chips for the country. And all the college people also slowly you can come up, and slow and steady always wins the race. But you should make your own amplifiers, your own simple outside the vacuum. At least you do. We don't have a lock-in amplifier. We don't have a power supply. We can't make RF. We can't make a laser. We can't make a plasma gun. How is it? So semiconductor manufacturing is integrated in the chip design and the system design, not only vacuum system, other systems. It all depends on the cross-disciplinary thinking, interdisciplinary thinking. If you are good, and if you are clean, and if you are a little bit intelligent, careful, very soon we are going to have Indian-made laptops, Indian-made cell phones, Indian-made TVs. Thank you very much. Next slide. So then on the chip, there will be India. Okay. Thank you so much.
Thank you so much, sir. It was such an inspiring session, I would say, such an informative session. And I thank you for the time and effort you have put in preparing these sessions and delivering it. Thank you. Really appreciate it, sir, from my heart.
Thank you so much.
Thank you, sir. Ishika, we can take the questions if any. Please raise your hand.
One thing great, after doing my puja, now I am getting appreciation from Puja Sabarwal madam.
And sir, I really appreciate. I think you are fasting and giving the lecture with so much energy. I appreciate
No,
it.
thank you.
It was so informative.
Thank you. So because no, inside also if vacuum is there, it's good.
Bhavnari is there and Rama Shankar.
Ma'am, I have disabled their mics. They can speak.
Yeah, Bhavnari, you can please take forward
Thank
your
you, ma'am.
question.
Good evening, sir. Thank you very much for a wonderful and informative and encouraging talk. Sir,
Thank you.
I would like to know, could you suggest some books related to this area where we can learn about the system design, vacuum systems importance and how, because you are told like various shapes as well as the valve size in between the diffusion pump as well as the chamber.
Yeah. Okay, what I will do, I will pass on some list of books to Puja madam, and I hope she will be able to send it to you. There are very
Thank
good books, headline in high vacuum technology. You just net, if you put ultra high vacuum technology for semiconductor manufacturing or vacuum technology, you will get so many books. I have written long back 100 rupee book that is called Vacuum Science and Technology. But because nowadays $100 books are available, but I want to make 100 rupees. And later we can together write also some books concentrating on one aspect. If you want to really serve this country, we have to make available a lot of materials. And this university is doing a very good job, and they should further proceed with writing some small bulletins, books, monograms. Okay. So I will send it. Madam, kindly remind me by WhatsApp message. I will add some
Sure,
15, 20
sure,
books, which is
sir,
meant for
sure,
what,
sir.
etc. And
Sure, sir. We will
bring it
take
to.
it forward under your guidance, sir. How to write the memo, taking
Yeah.
forward this topic. Yeah.
Thank you,
This
sir. Sir,
FDP, I would also tell the participant, this learning won't stop here. We all are connected now and we have to take the things forward.
Yeah. It's not short-term course. It's have a long-term effect.
It is a long term, yeah. Yeah, Rama, Mr. Rama, you can please take forward.
Thank you, sir. Good evening.
Good evening.
From this side, Ramesh Shankar, sir.
Okay.
My question is, sir, how we can select a right combination of pump to achieve
Yeah.
desired pressure and speed of pump?
Yes. Yes. Supposing your system is demanding a particular flexibility, you have to have some 1 meter long because it is in AC room, somewhere else it is there. You don't want that sound or something. Then we'll have to intentionally increase the pumping speed. Otherwise, effective pumping speed available is less. So all that you need to do is you look at the chamber, take it as a chamber volume V, and but look at the diagrams of the manufacturers. They will give you whenever you purchase don't purchase anything. Ask them what type of pumping speeds you are making. First rotary pump, most likely you will be purchasing two pumps. One is rotary pump, one is turbomolecular pump. Ultra high
Yes.
vacuum cryo pump right now you are not going to. And most of the time you are using 1 inch pipe, 2 inch pipe of 1 meter or to 1 foot. And most of the time chambers are half a meter cube or 1 meter. So these three things are fixed. Now clamps are CF clamps or KF flange couplings. Somebody has to tell components. I hope somebody will tell. So you have to decide which company is manufacturing what. Once you decide that 200 liters, most of the Indian companies manufacture 300 liters per minute type thing. More, then use that. And most of the pipings are 1 inch pipes of half a length. So you know the conductances, calculate the effective pumping speed, use that pumping speed VDP by dt, the S into P, then whether you will, that is good enough or not. If it is not good enough, then you either increase the pumping speed or increase the conductance. or
Yes.
reduce the outgassing. So which one is to be done? There is no single solution. It Somebody can afford to, if it is a bulb evacuation, the leak tightness is very important. If it is a big TV tube, then even if there is a small leak, after 1 year, 2 years, it will come to the atmosphere. So depending on the affordable leak rate and the atmosphere, you need to check. If the quality of the vacuum pump need not be high, but quantity should be high, or you can connect two pumps in parallel to get maximum. Don't purchase a large pump just because the calculation is giving such high pumping speed. You make two pumps parallel. Sorry, I forgot. It's a very good point that you have raised. Two pumps parallel, 300, 300. You will get 600. And when it is not required after getting 99.9, now you can go back to one pump because it is doing a business of backing the turbo pump. It is not doing the roughing of the chamber. So you can reduce 2 kilowatts power continuously for the next 10 days. So parallel pumps create more pumping speed. Series pumps create more compression ratio. That way you will get better vacuum to connection. So when to use parallel series connections, whether it is the connecting pipes or pumps, or when to use the high quality chambers or normal couplings, it is your decision.
Thank you very much.
Thank you so much, sir. Ishika, please take it forward now.
We extend our sincere gratitude to Professor V.V. Rao for sharing their vast industry experience and technical expertise. Your insights have not only deepened our knowledge, but also inspired us to explore new possibilities in this domain. Thank you for being a part of this program, sir.
Thank you very much.
Thank you so much, sir. Thank you so much for your effort and time, sir.
No. If anybody is planning to
Thank
do
you.
any system, you give your rough sketch of the system and you make a rough diagram, rough design. I will correct it.
Thank you so much, sir.
Thank
Thank
you
you.
so much.
Thank
Bye.
you, sir. So we can start for the next session now.
Yes.
Yeah.
Our next session explores a critical aspect of semiconductor manufacturing, vacuum technology in IC fabrication. We are honored to welcome Professor Mohammad Javed Siddiqui, a distinguished expert in electronics engineering from Aligarh Muslim University. With extensive experience in semiconductor devices, VLSI design, and microelectronics, he has significantly contributed to the field of semiconductor technology. He will provide a foundational overview of key principles of vacuum technology in integrated circuit fabrication and discuss the role of vacuum pumps. This session will serve as a refresher while setting the stage for a deeper dive into advanced processes tomorrow. Without further ado, we invite Professor Muhammad Javed Siddiqui to take the virtual stage and share his insights with us.
Thank you.
Welcome, Dr. Muhammad Siddiqui.
Thank you very much
It will be a pleasure for us to listen you.
for your kind invitation and giving me the opportunity to discuss the use.
I think the voice is gone, isn't it, Ishika?
Yes, ma'am. I guess there's some network issue from sir's side.
We can wait, or Dr. Anu, you can please check with the sir once. You can share the slides, Ishika, meantime.
Yes, ma'am, I'm doing that.
Hello everyone. Am I audible or not? Hello.
Yes,
Yes,
sir,
sir, you're
audible
audible
now.
now.
Yeah.
Okay. Can I know about the participants from which background they are? Because that will help me to discuss these things. Generally, they have the electronics background or some other fields. Hello.
Yeah, sir.
Yeah.
So you are audible.
Can I know about the participants from which background they belong?
So they basically belong from the manufacturing, mechanical engineering, electronics engineering, I would say. Maximum
Okay.
from the electronics engineering.
Okay. Thank you very much. So, good evening to all. As you know, I am Dr. Mohammad Javed Siddiqui, Professor in Department of Electronics Engineering. So, I will be discussing the vacuum technology. Vacuum technology is very old technology, and the uh, in the past, the electronic devices which were used in World War One and World War Two, they were based on the vacuum technology. You may be heard about the name of the vacuum diode, vacuum triode. All these devices were based on the vacuum. So vacuum is uh, that is the space which is void of the material, and material is removed so that we don't have the scattering. The one of the very important parameter in electronics is the mean free path. So in free space or in vacuum, the mean free path that increases, that is the charge or any particle can travel a distance without collision. That is the average mean free path is one of the very important parameter in electronics. So that was created in the devices like the diodes and triodes. Please go to the next slide. Please go to the next slide. Yeah, so these are the contents of my presentation. Previous one, previous one, previous one. Yeah, these are the contents. Use of vacuum in electronics, then vacuum devices, briefly vacuum diode, triode, and then briefly we will go into the solid state devices, introduction to the semiconductors, and then we will discuss about the germanium and silicon, because these are the two important semiconductor material which are used extensively in integrated circuit fabrication. So briefly we will discuss about the germanium and silicon. Then the how the silicon is extracted from the silica, extraction of the silicon from the silica, and then how wafers are uh, they fabricated from the CZ and FZ technology. Then the important electronic devices, these are the BJT and MOSFET. So briefly we will discuss about the BJT and MOSFET, and then we will come to the integrated circuits and their fabrication, and importance of the clean room environment, how contaminants affect the yield. So these uh, things we will discuss, and then we will discuss about the vacuum evaporation, use of the vacuum pumps in integrated circuit fabrication, and lastly the conclusion. So now, yes, please go to the next slide. Yes, please go to the next slide. Yeah, use of vacuum in electronics. Vacuum technology played a crucial role in the development of early and modern electronics. It was primarily used in vacuum tubes, also known as the thermionic vials, because in the vacuum tubes, the the electrons they are generated with the help of the thermionic emission. So, and that continues to Yes, I'm audible. Huh? Okay, okay. So vacuum diode, that is the uh, one of the very early device, electronics device, and then the but in the vacuum diode, actually that is just like work. It works like the valve. It provides the one directional flow of the current. So that was not very useful. So then a grid is placed, and the next device which came into the picture was the vacuum triode. And vacuum triode was very helpful in amplification of the radio signals at that time. Even now, in microwave range, especially in the transmission of the microwave signals, RF signals, even now these vacuum triodes, tetrodes, pentodes, and titrons, these devices are still very popular in high power transmission, where we transmit the signal over the environment for a long distance. So high power is needed. So high power we cannot transmit with the help of the solid state devices. That we can transmit with the help of these vacuum devices. So the vacuum devices are still used, and one of the very popular uh, uh, the equipment which we frequently use in our labs, that the cathode ray tube CRT. CRT is one of the very important equipment, and which is used in extensively in electronics lab. So that is also based on the vacuum, uh, and frequently this then CRT is used in early televisions and computer monitors. They were made using the CRTs, and then oscilloscopes and in the radar displays. Earlier the radar displays they were using these CRTs. Yes, please go to the next slide. Yes, please go to the next slide. So vacuum electron devices for high power application. Vacuum tubes are still used in applications where high power, high frequency, and high efficiency are required. One of the very popular devices is the magnetron. Used in microwave, even magnetron is also used in microwave oven and radar system for generating microwave signals. Then klystrons and traveling wave tubes, all these uses the vacuums. Gyrotrons, X-ray tubes. X-ray tubes work by generating rays through high energy electron oscillations in a vacuum. Essential in medical imaging, industrial inspection, and security scanners. Vacuum chambers in semiconductor manufacturing, they are very popular in various integrated circuit fabrications. We use, generally we want to deposit the various layers, and these layers can be deposited with the help of the vacuum deposition techniques like physical vapor deposition, and also the low power chemical vapor deposition, low vacuum LPCVD, and all these things. So electron microscope, that is also one of the very important equipment which are used, uh, and that also require a high vacuum. That is used is scanning electron microscope, use vacuum for high resolution imaging, used in semiconductor chip production, scientific research, and material analysis. Space simulation and particle accelerators. Space environment simulators use vacuum chambers to test satellite components. Particle accelerators like the large hadron collider require ultra high vacuum conditions to prevent air interference with particle movement, and that is used in the aerospace. Yes, please go to the next slide. Yes, please. I'm audible. Hello, I'm audible.
Yes, sir, you are audible.
Please go to the next slide.
So there's a lag.
Yes. Hello. Yes. So vacuum devices, briefly we will discuss the vacuum devices, vacuum electronic studies and generation of control of charged particles in the vacuum. Please, next slide. Please go to the next slide. Yeah. So working principle, briefly we will discuss the working principle. Please go to the previous slide. Please go to the previous slide. Yeah, vacuum electronics operates on the principle of electron emission and transport in a vacuum without significant collision. So vacuum is actually created to avoid the collision, because collision will change the path of the electron. So that is why vacuum is created inside the vacuum electronic devices. This allows for high speed electron movement, amplification and power generation in various electronic devices. The key components of vacuum devices are cathode. Cathode is a heated element that emits electrons due to thermionic emission. When the cathode is heated, electrons gain enough energy to escape from the surface of the material, and that is known as the thermionic emission. This, this is known as thermionic emission. Then these electrons are collected by the anode. The anode is a positively charged electrode that attracts the electrons emitted by the cathode. The flow of electrons from cathode to the anode constitutes the electric current. And we can modulate these electrons with the help of the grid. So grid is one of the very important electrode, you can say, which is used in the triode to amplify the signal. So in more complex vacuum devices like triodes, a grid is placed between the cathode and anode. The grid is a mesh-like surface that controls the flow of electrons. By applying a voltage to the grid, the current between cathode and anode can be modulated, allowing the devices to amplify the signal. So basically, it's similar to your BJT, which has a three terminal like emitter, base, and collector. Similarly, the triode has the three electrodes: cathode, anode, and grid. Yes, please go to the next slide. Yes, please. Go to, yeah, so that is the comparison between the traditional vacuum electronics and general vacuum electronics. Uh, Traditional vacuum electronics that require high vacuum, and the general vacuum electronics include the nano vacuum devices that work with minimal vacuum. The electron transport in traditional vacuum electronics, electrons travel freely in vacuum, avoiding collision, while in general vacuum electronics, nano scale electrons channels enable near ballistic transport. Actually, in nano electronics devices, the transport mechanism for the electron is not diffusive. In diffusion, the electrons they collide with the other charged particles like the holes and ions. But in nano scale devices, the generally the transit time is very small and the channel is very short. So the electrons they travel just like a bullet, and that moment is known as the ballistic transport. So the traditional vacuum devices, these are the diodes, triodes, magnetons, etc. And nano vacuum devices that consist of the nano triodes, MEMS-based vacuum devices. Operating principle in case of the traditional vacuum electronics, that is the thermionic or field emission controlled by electric fields and grids. In nano, that uses the nano gaps or advanced material for efficient flow of electron. I have told you that the ballistic flow that is occur in nano electronic devices. So since okay, and power consumption in traditional vacuum, that high power is needed, and in nano electronics low power is needed. Application, as I told you, these vacuum devices, they are very popular in RF amplifiers, microwaves, etc. And these nano electronics devices, high speed electronic devices, they are used in like mobile and all these devices. And advantages: high power handling. As I told you, for the transmission of the RF signal, we need high power. So high power can be transmitted only using traditional vacuum electronics, not using the nano electronic devices. So, as we know that these devices are bulky. As I told you, in my childhood, I have seen a radio receiver set that will be the size of the desktop computer, like that, a big size radio receiving set. Because in that radio receiving set, the vacuum devices were used. So that vacuum devices, they are bulky and they use high power. But in nanoelectronic, of course, the fabrication complexity is there. So please go to the next slide. Yes, please go to the next slide. Please go to the next slide. Yeah. So I already told you the vacuum diode has the two electrodes only, cathode and anode, as shown in this figure. So this application of this vacuum diode that used in radio receivers and transmitters, I told you in my childhood, like in the, around 50 years ago, they were used in radio receivers and RF application, microwave applications. So, and at that time, they were also used in AC to DC converter, used in high voltage and high power applications where semiconductor diodes may not be suitable. Yes, please go to the next slide. Please go to the next slide. So vacuum triode, I told you, that is similar to our transistors, BJT and MOSFET, which have three terminals. So vacuum diode we cannot use for the application purpose, but vacuum triode can be used as an amplifier. We can amplify the signal and we can transmit the signal. So this vacuum triode, it uses an additional electrode in the form of the grid by which we can modulate the signal. You know, the modulation is one of the very important phenomena which is used to transmit the signal over large distances. So modulation you can do in case using vacuum triode, not using the vacuum diode. Yes, please go to the next slide. Please go to the next slide. Yeah, so after these vacuum devices, in 1947, first solid state device that was manufactured by Bardeen and Walter Breton and William Shockley at Bell Labs. That was the point contact transistor that consisted of germanium crystal with two closely spaced metal contacts, and that was used to amplify the electrical signal by controlling the flow of current through the semiconductor material. So that was the first solid state device. And after that, in 1948, William Shockley invented the BJT, bipolar junction transistor. As you know, that this bipolar junction transistor, that is are of two types, NPN or PNPN. In NPN transistor, the P layer is P-type semiconductor is sandwiched between two N layers, and in PNP transistor, N-type semiconducting layer is sandwiched between two P-type layers, but doping in all these three layers is different. So that is provide better performance and reliability than the point contact semiconductor transistor. Yes, please go to the next slide. Please go to the next slide. Yeah. And later on in 1952, the field effect transistor was developed. We developed using controlling the current with the help of the electric field. That includes the variants like junction field effect transistor, which now became obsolete, And now one of the popular transistor is the metal oxide semiconductor field effect transistor, MOSFET. MOSFET became very popular because of the one reason, and that is due to the power consumption. As you know, earlier the fastest technology was the ECL, emitter coupled logic, using that was designed using the BJT. But later on, the CMOS became very popular because that required a very small amount of power. Dynamic power, static power in case of the CMOS is almost zero. Dynamic power is there. Dynamic power means when state is changing either from 1 to 0 or from 0 to 1, then only current flows and some dissipation occur. So that is why the junction field effect, the field effect transistor MOSFET was become very popular. Semiconductor diodes, early solid state diodes was manufactured using germanium, and later on that was manufactured using the silicon, and that replaced the vacuum diodes for rectification. And the material used earlier, the early semiconducting material was germanium, because in 1948 and 1940s, 1950s, the silicon was not available in its purest form. It was available in plenty of silicon was available in the form of the silica, but germanium was available at that time. So germanium was utilized to manufacture the transistors and diodes. But later on, germanium was replaced by silicon because the thermal stability of germanium was very poor. Of course, the germanium has more mobility and has less energy gap. The thermal stability of germanium is very poor with respect to silicon. So that is why silicon completely replaced the germanium. Advantages of the solid state device: small size, low power consumption, durability, long lifespan, efficiency. So that is why the solid state devices replace generally the vacuum devices. But I have told you that the vacuum devices are still used in where we need large power. So please go to the next slide. Please go to the next slide. Yeah. So almost in all walk of life, the solid state devices became very popular in radios, television, computers, telecommunication, industrial control, and these are the milestones in the solid state technology. In 1947, the first transistor was invented. In 1954, the silicon transistor was introduced by the Texas Instrument. In 1958, the first integrated circuit was made by the Texas Instrument and by Fairchild also. So mass production of transistor and ICs, integrated circuits, that was produced in 1960s. So impact on the modern electronics: solid state devices laid the foundation for the modern electronics, including the microprocessor, memory chips, sensors, enabled the development of portable devices such as smartphones, laptops, and wearable technology, revolutionized industries like telecommunication, computing, and consumer electronics. And the main role that was played by the miniaturization of these solid state devices. Earlier, the size of the transistor, the MOSFET, the channel size in 1980s was around in the range of the micrometers, 10 micrometers, 100 micrometers, something like that. And the electronic industry that follow the Moore's law and the miniaturization. Due to miniaturization, the size of the solid state devices that is decreased almost half in 18 months. Please go to the next slide. Yes, please go to the next slide. Yeah, briefly we will discuss about the semiconductor. What is a semiconductor? A material with electrical conductivity between conductors and insulator. That is why it is called the semiconductor, because it is in between insulator and semiconductor, good conductor. Foundation of the modern electronics, that is transistors, all the integrated circuits, they are made using the semiconductors. So the key characteristics of the semiconductors, in this figure you see, in this figure the energy band diagram for conductor, for insulator and for semiconductor is given. The for conductor the energy gap is zero. The conduction band and valence band both are overlapping each other, and in general semiconductors they have the energy gap in the range of 0.1 electron volt to 3 electron volts, and if energy gap is more than 3 electron volts, then that material behaves as an insulator. So generally the band structure is the small band gap less than 3 electrons allows the electron movement under certain conditions and temperature dependence. Insulator at 0 degree Kelvin, all the states in valence band are filled and all the states in conduction bands are empty. So no electron is available for conduction of the current. So at 0 degree Kelvin, semiconductor behaves just like the insulator. And these pure semiconductors, they are of no use. That is, to make these semiconductor devices, we use the doping, N type or P type. N type, like phosphorus from the fifth group is added to the silicon or germanium, or for P type, generally boron from the third group of the periodic table is added to the silicon or germanium. Please go to the next slide. Yes, please go to the next slide. Yes. So you know that intrinsic semiconductor means pure semiconductor without doping. Please next. Yes. Yes, please.
Sorry, sir, there's a network issue from our side. I'll
Okay.
just share.
Okay, no problem. Okay, no problem. Okay, no problem.
Sir, is the screen visible now? Is
Yes,
my screen
yes,
visible?
yes, yes, visible, visible.
Yes, sir.
Yeah,
Thank you so much, sir.
yeah. So as I told you that extrinsic semiconductor, these are the semiconductors with impurities. For N type, we have the impurities from the fifth group of the periodic table like phosphorus. And for P type, we have the impurities from the third group of the periodic table like boron. And examples of semiconductor materials, generally three types of semiconductor materials are very popular. Silicon, widely used in electronics. 50, 90, 90, but 98% or 99% electronic devices and integrated circuits, they are manufactured using silicon. Germanium is used in very special cases like some special photodiodes, etc. And then compound semiconductors, they are very important. The gallium arsenide, indium phosphide, silicon carbide, these are the compound semiconductors, and especially in optoelectronic devices like the fabrication of the laser diode or LED light emitting diodes. Generally, these diodes, light emitting diodes and laser diodes, they are fabricated using gallium arsenide because that is a direct band gap semiconductor material. So, on recombination of electron and holes, the photon is emitted, light emits, and in direct band gap semiconductor, recombination is very easy. Silicon and germanium both are indirect band gap semiconductor materials. So there, for recombination, first electron has to relieve the momentum, and then it can recombine with the hole from the valence band and emitting the light. So gallium arsenide is very popular for optoelectron devices. Yes, please go to the next slide. Yeah. Next. Yeah. Next.
Yes, sir. I don't know why is this happening. Slides are moving really fast.
Okay. Okay, no problem, no problem.
Sir, is the screen visible now?
Yes. Now it is visible. Yes, please. Okay. So, as I have told you that these semiconductor materials, especially the silicon, that is very popular in rectifiers and in amplifiers and other integrated circuits. Advantage of the semiconductors stability enables miniaturization of the device. As I told you that the electronics industry that follows the Moore's law, and that states that the size of the device that become half in every 18 months. So that is the miniaturization. Energy efficiency, consume less power, versatility, applicable in diverse fields, cost effective because integrated circuits are produced in bulk. So installation and the capital cost of integrated circuit fab is very high, and running cost is also very high. But per chip cost that become very small because these integrated circuit chips, they are produced in bulk. So per chip cost become generally very small. Yes, please go to the next slide. Yeah, just a brief conclusion of the silicon germanium. As I told you, the early semiconductor material was germanium, but later on, the germanium was replaced by the silicon, and that is why? Because germanium has energy gap of 0.7 volt. So it has a small the breaking voltage. Breaking voltage means what maximum voltage we can apply to the semiconductor. So silicon has a band gap of 1.1 electron volt. So high voltage can be applied to silicon devices, but we cannot apply the high voltage of the germanium devices. Thermal stability in case of the silicon that is higher, and germanium it is lower. Electron mobility in case of germanium is high. That is why still in some special devices germanium is used. Mobility, you know that mobility is directly related to the transconductance, and transconductance is directly related to the voltage gain. And in application, we generally need high gain, high voltage gain. So high voltage gain that we can obtain with the high mobility, but other parameters are also important. So in case of germanium, mobility is high, but thermal stability is very poor. That is why it is not used. And one of the advantage of silicon over germanium is that the silicon dioxide, it is a very good insulator, and this is very important. You can say the device. It is very important in device applications because it can be grown directly just heating the silicon wafers in a surface in a furnace. We can grow silicon dioxide very easily, and silicon dioxide is very good insulator. So in MOSFET directly we can grow silicon dioxide, and MOSFET, as I told you, that because of the CMOS, it has the power efficiency is very good. So we can easily fabricate the CMOS devices in which silicon dioxide is needed. So silicon dioxide has very advantage over the germanium. That is why the germanium is almost replaced by the silicon. High speed application, of course, in germanium, as I told you, that mobility is high, so it can be used, and it has the excellent use in the high speed application. And abundance of silicon is more because silicon is available from silica, that is sand. We can extract silicon from silica very easily. Yes, please go to the next slide. So next slide is based on the extraction of the silicon from the silica. Silicon extraction from silica, silicon dioxide is the key industrial process, as silicon is a critical material for semiconductor. As I told you, the whole electronics industry is based on silicon. And the contribution of silicon in the electronics industry is almost 90 to 95%, and in some cases 98%. So the silicon is one of the very important material which is needed in electronic industry, and it can be very easily extracted from the silica, and it is a critical material for semiconductor, solar panels, and other technologies. The most common method for extracting silicon from silica is the carbonic reduction process, which involves the reducing silica with carbon at high temperatures. Below is an overview of the process. First, raw material. Raw material is the silica, typically sourced from quartz or sand. Carbon is required because when silica react with the carbon, so carbon dioxide that is produced, and silica is converted into silicon, usually in the form of the coke or charcoal or coal, which acts as a reducing agent. Carbothermic reduction process, the chemical reaction is given here. The silicon dioxide, it reacts with the carbon, making the products are silicon and carbon dioxide, carbon monoxide, etc., which can be emitted from the furnace. Preparation of the raw material, silica and carbon, are finally ground and mixed in the correct stoichiometry ratio. Impurities in the silica, such as iron, aluminum, and calcium oxides, are minimized to ensure high purity silicon. Heating in an electric arc furnace. The mixture is heated in electric arc furnace at temperatures ranging between 1700 degrees centigrade to 2000 degrees centigrade. Then this reduction process occurs. The chemical reaction is given in this slide. So as a product, the silicon and carbon monoxide that is in the form of the gas, so that will be vented out. Yes, please go to the next slide. Yeah. So separation of the molten silicon. The molten silicon settles in the bottom of the furnace due to its high density. Impurities that float on the top and can be removed easily by cutting the from more. Refining the extracted silicon is further purified to remove the residual impurities. This is often done through process like chemical purification using hydrochloric acid or other chemicals. Zone refining, a method to achieve ultra high purity silicon for semiconductor application. That is the float zone method is used. Generally, this silicon which we obtain from this reduction is known as the metallurgical grade silicon. The product of this process is the metallurgical grade silicon, MG silicon, metallurgical grade silicon, which is about 98 to 99% pure. Then this can be used in industries like aluminum alloys and silicones, and production of high purity silicon, because this Mg silicon we cannot use for the fabrication of the integrated circuits. For fabrication of the integrated circuits, we need electronic grade silicon. So for applications like semiconductor in solar panels and integrated circuits, we need 99.9999%, 6M or higher. This is achieved through conversion to trichlorosilane. This is SiHCl3. Metallurgical grade silicon is reacted with hydrogen chloride to form trichlorosilane, and then distillation process is used to purify and to remove the impurities. Yes, please go to the next slide. So that is the schematic of extraction of the silicon from the silica process that is shown, and that we can do in the using the chemical vapor deposition also. In some applications we need to deposit the silicon on vapor, so that can be deposit with the help of the trichlorosilane in a chemical vapor deposition chamber. Yes, please go to the next slide. Silicon crystal growth, that is very important. Generally, silicon is available in three forms: amorphous silicon, polycrystalline silicon, and single crystal silicon. Uh, amorphous silicon is a pure disordered material having very poor mobility. Rarely it is used for the fabrication of the electronic devices. In some special applications like large area electronics, sometimes amorphous silicon wafers are used there. But in general, all the electronic devices and all the integrated circuits are fabricated on single crystal wafer. So just briefly, we will discuss about the amorphous silicon, polycrystalline silicon, and single crystal silicon. Single crystal silicon has the highest mobility. Amorphous silicon has the poorest mobility, and polycrystalline silicon that contains the grains of are crystals, small crystals of silicon. Within the grain, they have the orientation of the atoms in a desired position, but in other grain, the orientations of the atoms will be different. So, and between the grain boundaries, we have the discontinuities. So, polycrystalline silicon material that has the mobility in between amorphous silicon and single crystal silicon. Single crystal silicon, suppose that has the mobility of around 1000 centimeter per volt second, while the polycrystalline silicon may have the mobility in the range of the 10 and 10 to 100, and amorphous silicon may have the mobility 1 or less than 1. So all the electronic devices, they are fabricated on single crystal silicon because that has the good mobility. As I told you earlier, that mobility is one of the very important parameter of the electronic devices, because in case of the transistor, in case of the MOSFET, the mobility is directly related to transconductance, and transconductance is directly related to gain of the amplifier. So that is why all electronic devices are fabricated using single crystal silicon. So these single crystal silicon, they are grown by different methods: CZ, the velocity method, or float zone method, that is known as the FZ process. So silicon crystal growth is a critical step in the production of high purity silicon for semiconductors, solar cells, and other electronic applications. The most common method for growing silicon crystal is the velocity CZ process, which produces single crystal silicon ingots. From ingots, we can cut the wafers. Another method is the float zone, which is used for ultra high purity silicon. But in F zone method, the size of the wafer is limited. So in CZ process, that is most widely used method for growing single crystal silicon ingots, it involves pulling a seed crystal from the molten silicon. These are the steps which are used in CZ process: melting high purity polycrystalline silicon that is placed in the quartz crucible. The crucible is heated to a temperature above melting point. Melting point of silicon is around 1400 degrees centigrade in an inert atmospheric uh, environment to prevent the contamination. Contamination, because they play a very important role in the semiconductor manufacturing. They affect the yield. So we should be very careful about the contamination. Contamination should not contaminate the wafers or in, and also in the processes which are used on the wafers. So seed crystal is placed, a small crystal, single crystal silicon seed oriented in the desired crystallographic direction, that is 100 or 111, is deep into the molten silicon, and then it is slowly pulled. Crystal pulling. The seed crystal is slowly pulled upward while rotating. As the seed is pulled, molten silicon solidifies at the interface, forming a single crystal ingot. Yes, please go to the next slide. So diameter, you can control the diameter of the ingot is controlled by adjusting the cooling rate and temperature. Typical ingot diameters ranges from 150 millimeter to 300 millimeter. Now it goes to beyond 12 inch. And cooling, the grown crystal is slowly cooled to room temperature to prevent thermal stress and effects. Of course, at the same time, dopants may be added to the pure silicon. If we sometime we need the wafers which are N, N, N type dope and some P type dope, or sometimes intrinsic wafers are needed. So depending upon the need, we do it. If we need the N type wafer, then I told you phosphorus may be added. If we need the P type, then boron may be added. Advantage is this: the high production yield, suitable for large diameter crystal, cost effective for semiconductor and solar applications. This is advantage. Oxygen continuation from quartz crucible. Limited purity compared to float zone process. Yes, please go to the next slide. Yeah. So in float zone process, we can produce a good quality, ultra high purity silicon ingots. So float zone process is used to produce ultra high purity silicon crystals with minimal contamination. This is particularly important for high performance semiconductor devices. These steps: polycrystalline silicon. A rod of high purity polycrystalline silicon is placed vertically in a chamber. Zone melting. A small section of the rod is melted using high frequency induction coil or laser heating. The molten zone is moved slowly along the length of the rod. The single crystal formation, a single crystal seed is placed at one end of the rod. As the zone moves, the silicon solidifies into single crystal behind it, and dopants can be introduced into the molten zone to control the electrical properties of the crystal. Advantages: extremely high purity because here we don't have the crucible contamination. So the ingots and the wafers are very, very pure. Low oxygen and carbon content, ideal for high power and high frequency devices. Just please go to the next slide. This is the figure which is used for the FZ crystal pulling, and that is the temperature. Purity in float zone process, so purity is very high, but size is limited. We cannot go beyond 150 millimeter. But in the closely process, we can go up to 300 millimeter or even up to 12 inch. Oxygen content in CZ is high, in FZ it is low. Cost in CZ is low, in FZ cost is high. Applications, CZ process wafers can be used in semiconductor solar cells, and FZ process may be used to, these wafers may be used in high power devices and for research. Yes, please go to the next slide. Yes, as I have told you in the beginning, the heart of the integrated circuits is either BJT or MOSFET. BJT is, that is the bipolar junction transistor. In BJT, the current conduction is because of the both majority carriers as well as the minority carriers. While in MOSFET, that is a unipolar device, so only the current is carried by the majority carriers. If it is carried by the electrons, then we have the N-channel MOSFET, and if it is carried by the holes, then it is P-channel MOSFET. So a BJT is a three-layer semiconductor device consisting of two chain junctions. It has three terminals: emitter, base, collector. Most of you know about the BJT and MOSFET, so I'm just skipping it. Please go forward. Please go to the next slide. Yeah. That is the working principle of the BJT. Our emitter is heavy doped and supplies the charge carriers, electrons in NPN transistor and holes in PNP transistor. A small current applied to base allows a large current to flow from collector to emitter. Actually, the signal applied at the base that can be used to amplify. We can amplify that signal. A small change in base emitter voltage will produce a large change in the collector current. That is just a minute. Just a minute. Yes, sorry, please. We will continue. So these are the modes of operation of the BJT: cut-off, active, saturation mode. Active mode is very popular for amplification purpose, and cut-off and saturation, they are used in switching. BJT, PNP BJT is not very popular because holes have the lower mobility than electrons. And these are the applications of the BJT. Just please go to the next slide. The most popular MOSFET is the enhancement mode MOSFET. In enhancement mode MOSFET, we can enhance the current. Channel current is enhanced by applying large gate voltage. So that is why it is enhancement type MOSFET. If we increase the gate voltage, the current in channel will increase. That is, and in depletion type MOSFET, already channel is there, and by applying the opposite voltage on the gate, the current that will decrease, and depletion region that will increase. So that is the depletion mode MOSFET. Depletion mode MOSFET is not very popular. And again, in this we have the triode region and the saturation region. In MOSFET, we have the two regions only. The triode region, which is also known as the linear region, Cutoff, you can say, if the VTH, the threshold voltage, the gate voltage is less than threshold voltage, then it is in cutoff, no current will flow. So that is the cutoff. And if we apply voltage more than gate threshold voltage on gate, then it will start conducting. And initially, that current is proportional to voltage between drain and source. So that is why it is known as the linear mode. And then after a certain voltage, the current saturates. That is known as saturation. And these are the various applications of MOSFET. Just please go to the next slide. These are the various advantages and disadvantages of BJT and MOSFET. BJT is a current control device. MOSFET is a voltage control device. Switching earlier in the 1980s, the BJT was the fast, because in the emitter coupled logic that was used, that was the fastest logic family at that time. But later on, due to miniaturization, the MOSFET became faster. Power consumption is higher because of the base current, and in case of the MOSFET, it is low due to high input impedance. Because between the gate and channel we have the insulating layer, so gate current is almost zero. So that has the high impedance, so it is power efficient. Thermal stability in case of MOSFET is good. Efficiency, cost, and input impedance, application suitability. BJT is suitable for analog applications, and MOSFET is very much suitable for switching applications. In digital applications. In digital applications like the microprocessors, memory, generally they are fabricated with the help of the MOSFET. Yes, please go to the next slide. That is the construction of BJT and MOSFET. Yes, please go to the next slide. Yes, now next is the integrated circuit. Integrated circuits are the building blocks of the modern electronics, enabling the miniaturization and integration of complex electronic circuits on a single chip. The fabrication of integrated circuits is highly intricate process that involves multiple steps and advanced technologies. Below a detailed explanation of integrated circuits and their fabrication process. Introduction to integrated circuit definition. An IC is a set of electronic circuit on a small piece of wafer, chip, or semiconductor material, typically silicon. It integrates multiple components like transistor, diodes, resistors, capacitors into single chip. In the beginning of the electronic solid-state devices, generally these solid-state devices were connected and used as a discrete devices. Earlier, these discrete devices were used in the PCB, printed circuit board. In printed circuit boards, we generally form the circuits with the help of the discrete devices. A BJT is placed, then a resistor is placed, then a capacitor is placed, and individually we place these components on the PCB, and then soldering was used to solder to connect one component to each other. And this soldering is very highly unreliable, you can say, highly unreliable. Sometimes it seems that the emitter or collector of the BJT is connected to the load resistor, but the soldering is not good and it is not connected and our circuit is not working. These problems were removed with the help of the integrated circuits. In integrated circuits, all the components are fabricated on a single wafer at the same time. If we suppose we have the 10 BJTs, then starting from the collector, if we fabricate the collector of the transistors, then collector of the transistors of 10 BJTs that will be fabricated simultaneously. So all the components, they are fabricated, they are formed on the wafers simultaneously, and that contained in a single chip. Only we cannot see the components inside the integrated circuit. Just the output terminals are there. Output terminals that can be used to connect the input and output signal. So types of ICs, these ICs are very popular ICs, analog ICs, process analog ICs process continuous signals like operation amplifier, etc. Digital ICs process discrete signal, that is like I told you, microprocessor, memory chips, logic gates. These are digital ICs. Mixed signal ICs that combine analog and digital both. And now also we have the hybrid. In hybrid, we have the BJT's circuits and the MOSFET circuit on the same chip. Power ICs designed for the high power application. Advantage of ICs, miniaturization, thousands and to billions of components can be integrated to a small chip. On a wafer, we may have thousands of chips. So that is why it is very cost effective. Mass production reduces the per unit cost. High performance, faster operation due to shorter interconnect. Low power consumption, efficient design and smaller components reduces power usage. Reliability, fewer interconnection and robust fabrication process enhance reliability. As I told you, in PCB, the soldering joints are highly unreliable. But in integrated circuit, we don't have this problem. Yes, please go to the next slide. So briefly, we will go discuss the integrated circuit fabrication, and because the title of the talk is use of the vacuum technology in IC fabrication. So now we will focus on the integrated circuits and the vacuum technology. In IC fabrication, generally we start from the wafer preparation, then various layers are deposited. Patterning is done with the help of the lithography and etching. Sometimes we have to use the doping, like in the BJT. Suppose in the starting substrate is an N type, so we need doping to form the base. We need doping to form the emitter. So that is done. This doping can be done using the diffusion process or using the ion implantation. Metallization is done for connecting the integrated circuit to outside world, that is done with the help of the metallization. Then final testing and packaging. The fabrication process is carried out in a clean room to avoid contamination by dust or particles. Because contamination that will affect the yield. Yield of the process, that is how many good chips are produced uh, and how many chips are not working. That ratio gives us that we determine with the help of the yield. So IC fabrication starts from the wafer preparation. A silicon ingot is both using CZ or FZ method, where core silicon is melted and then the ingot is sliced into wafers using with the help of the diamond saw. The wafers are polished to a mirror finish to provide a smooth surface for fabrication. Please go to the next slide. Yeah, epitaxial growth in uh, uh, especially integrated circuits using BJT. There the epitaxial growth is very important. If we fabricate directly in the BJT on the wafers directly, then the problem of the collector resistor, which will affect the gain and various other parameters. Uh, so that is why generally on a low conductivity substrate, high quality epitaxial layer is grown, and that in that epitaxial layer we may fabricate the BJT. A good quality BJT may be fabricated in that epitaxial layer. So epitaxial layer is grown with the help of the epitaxy. Epitaxy is a crystal growth technique used in semiconductor manufacturing to deposit a high purity, defect-free crystalline layer over a substrate wafer. This layer maintains the same crystal structure as underlying wafer, making it essential for high performance electronic and optoelectronic devices. Why epitaxial is important? Epitaxy plays a crucial role in modern integrated circuit fabrication for the following reason: improves transistor performance by enhancing carrier mobility, allows precise doping control for ultra-thin layers, enables heterostructures with materials like silicon germanium, gallium arsenide, and indium phosphide, used in high-power devices like silicon carbide and gallium nitride based electronics, essential for FinFET and dynamic RAM to enhance strain engineering and data retention. So types of the epitaxy. Epitaxy can be classified based on the material type and growth conditions. Based on material, similarly, homoepitaxy, same material growth, the epitaxial layer and substrate both have the same material, that is silicon on silicon or gallium arsenide, used in CMOS, FinFET and power MOSFET. Heteroepitaxy. Different material is grown on different layers. The epitaxial layer and substrate are different, like silicon germanium or silicon, or gallium arsenide or silicon. That is the heteroepitaxy. Used in high-speed transistor, HEMT. HEMT is high electron mobility transistor. HEMTs are very popular in power electronic circuits. And heterojunction, bipolar junction transistor, HBTs are also very popular. Next. Yeah. So based on the growth technique, we can use the vapor phase epitaxy. Molecular beam epitaxy, it is one of the very important process which is used frequently in integrated circuit fabrication, and it uses ultra high vacuum. Now the vacuum technology is employed in molecular beam epitaxy, and using the molecular beam epitaxy, we can deposit different layers over different layers. Heteroepitaxy. Hetero layers means, as earlier we discussed, like the silicon germanium on silicon. So these layers can be easily deposited using molecular beam epitaxy, and layer can also be deposited using vapor phase epitaxy and chemical vapor deposition (CVD). CVD is one of the very popular process frequently used in integrated circuit fabrication for various layers deposition. So epitaxial growth techniques, uh, as we have told, vapor phase epitaxy, common for silicon and gallium arsenide ICs, use gas phase precursors to grow epitaxial layers. These are the process steps. Reactant gases like silane or SiCl4 or germanium H4 flows into the high temperature chamber. The chamber temperature is around 900 to 200 degrees centigrade. The gases react with the deposit monocrystalline silicon or germanium layer on the wafer. By controlling the gas composition, doping can be adjusted. Application, silicon germanium transistor for high speed CMOS, high voltage power MOSFET or HEMT that can be fabricated with the help of the vapor phase epitaxy. Yes, please go to the next slide. As I told you that vapor molecular beam epitaxy (MBE) used for precise atomic level growth performed in high ultra high vacuum around 10 to the power minus 10 torque. It is common for third, fifth group semiconductors like gallium arsenide, indium phosphide, and quantum devices. These are the process steps. Elemental sources, silicon, germanium, gallium arsenide. Separately, they are deposited, heated, and produce atomic beams. And the atoms travel in straight lines and deposit on the vapor. Growth is there. As I told you earlier, the vacuum produces the large mean free path. So directly, without interacting with other particles or without colliding with other particles, directly these atoms may be deposited on the wafer. Application: heterojunction, bipolar transistor, HEMT, LEDs, lasers. These are fabricated with the help of the NCU. Limitation is that growth rate is very slow, 1 micrometer per hour. Expensive and not suitable for mass production. Yes, please, next slide. Chemical vapor deposition, as I told you, it is one of the very important process frequently used in integrated circuit fabrication, and it uses high purity gases to deposit epithelial growth, epithelial layers, type of CVD, epitaxy, low pressure, LPCVD. In low pressure, generally the vacuum inside the chamber is in the range of the 10 to minus 3 torr, used for silicon, germanium, and strained silicon layers. Metal organic CVD used for gallium nitride, indium phosphide, etc. And these are the reactions. Yes, please go to the next slide. Defects in epithelial growth, even small imperfection in epithelium can degrade IC performance. Common defects are lattice mismatch. In some case, lattice mismatch is there. Happens in heteropetexy, gallium arsenide on silicon substrate that may have the lattice mismatch because both material they have the different lattice constants, causes strain and dislocation that reduce mobility, threading location, contamination, and dopant segregation, and these are the solutions. Just please go to the next slide. So these are the schematic of various epithelial processes: vapor phase epitaxy, molecular beam epitaxy, and chemical vapor diffusion epitaxy. Just please go to the next slide. Next, one of the very important process in integrated circuit fabrication is the oxidation. As I have told you that in MOSFET, oxides serve as a dielectric layer between gate and channel. So a thin layer of silicon dioxide is grown on the wafer surface by exposing it to oxygen at high temperature. We may use dry oxidation or wet oxidation. In dry oxidation, the quality of oxide is very good, but growth rate is slow. In wet oxidation, the growth rate is good, but quality is poor. So generally, in the where we need the thick dioxide, silicon dioxide layer, especially in oxide isolation of integrated circuits, where we need thick silicon dioxide layer that is grown first. Thermal oxidation, the dry oxidation is used, and over that we can use the wet oxidation. The good quality silicon dioxide layer is first grown by dry oxidation, and then a thick layer of silicon dioxide is grown using wet oxidation. So silicon dioxide acts as insulator and protects the silicon during subsequent steps. Next is photolithography, and silicon dioxide is a very good masking agent. It is a very good masking agent. It can be used in photolithography to in region where we don't need the doping, that will be covered with the silicon dioxide. And in photolithography, photoresist is used, and we can remove the material from where we want doping, and where we don't want doping, that the material has to remain there. That is done with the help of the etching. So different etching process are there. Wet etching, in which involve the liquid chemical solution that dissolves the export material. Advantage: simple, cost-effective, and high selectivity. Disadvantage: isotropic etching etches equally in all directions, which can lead to undercutting and less precise pattern. Applications used in materials like silicon dioxide, silicon nitride, and others. Yes, please go to the next slide. Dye etching. In dye etching process, plasma or reactive gases are used to remove the material. Common techniques include reactive ion etching, plasma etching, and sputter etching. Advantage: anisotropic etching. Etches primarily in one direction. Allows for more precise and vertical side bars. Disadvantage: more complex and expensive equipments are needed. Lower selectivity compared to wet etching. Application used for advanced nodes and complex structure in modern ICs. Key etching technique: reactive ion etching, combines chemical and physical etching, plasma etching, sputter etching. Yes, please go to the next. Materials commonly etched in IC fabrication: silicon dioxide, often etched using hydrofluoric acid. Hydrofluoric acid is very efficient for etching the silicon dioxide in wet etching. And silicon etched using wet chemicals like potassium hydroxide or dry etching techniques like rectified etching. Metals like aluminum and copper are etched using wet chemicals or plasma-based methods. Polysilicon etching uses fluorine or fluorine-based plasmas. Challenges in etching: selectivity, that is very important. In some direction, we need the etching; in other direction, we don't need etching. So selectivity is very important. Uniformity, that is also very important. Profile control, maintaining the desired shape and angle of the etched features. Application of etching in IC fabrication: gate formation, trench isolation, wire contact formation, metal patterning. Yes, please, go to the next. Yeah, so these are the figures showing the wet etching and dry etching. So in wet etching, you see the undercut are there, but in dry etching, undercuts are not here. Yes, doping, as I told you, that can done with the help of the diffusion or ion transition. Yes, please go to the next slide. And deposition, in deposition, we use generally two processes are very popular. The 1 minute, please. Sorry for interrupt. Sorry. So yes. जी हेलो. हाँ मैंने भी किया था. अब हेलो, आर यू? Yes. Uh, yes. Now I'm audible.
Yes, sir.
Okay. Okay. Due to limited time, now we will move to the slide number 60. Please, we don't have the enough time. We have so many slides, so we will cut short. So this is the, as I've told you, for layer deposition, two techniques are very popular: physical vapor deposition and chemical vapor deposition. In physical vapor deposition, the popular technique is the vacuum evaporation, that is carried out in a high vacuum. So this is the slide showing the vacuum evaporation. In vacuum evaporation, generally all the metals are deposited using vacuum evaporation. In vacuum evaporation, in high vacuum, the material is evaporated directly from solid phase to the gas phase. Yes, please go to the next slide. Now we are coming to the vacuum technology in IC fabrication. Briefly, we will discuss. You may have learned in previous lectures about the vacuums, but briefly we will discuss the how this vacuum is created inside the chamber and definition of the vacuums from atmospheric pressure to low pressure and to high vacuum. So definition, we will just briefly discuss the definition of the vacuum. Vacuum technology is the method of creating spaces devoid of matter, especially air, inside the chamber. Historical development. vacuum technology has evolved significantly from the 18th century to the 20th century. The importance of the IC fabrication crucial for process like the position of etching in semiconductor manufacturing, evolution of vacuum system, transition from basic system to sophisticated system capable of ultra-high vacuum, role of deposition and etching. In integrated circuit fabrication, this is very important, deposition of layers and etching of these layers where we don't need, and then achieving ultra-high vacuum. How the ultra-high vacuum can be achieved? Yes, please go to the next slide. So vacuum can be measured in millimeter of the Hg or inch of the Hg or torr or microns of the 1 inch of mercury, that is its units is 1. So measuring vacuum, as with any kind of measuring, requires standard units to measure: inches or millimeters of mercury, torr micron, 3 units of measuring typical associated with the vacuum industry. So generally torr is very popular because of the work of the 17th century scientists. So we said, we know that the atmosphere generally exerts enough pressure at sea level to support about 30-inch 760 millimeter column of mercury for that formation. So 76 millimeter of Hg, 1 millimeter of Hg is 1 torr. We can measure decrease in atmospheric pressure in terms of inches from millimeters of mercury. Thus 10% drop in atmospheric pressure would indicate 3-inch fall in the height of our column of mercury. In this way, vacuum came to be measured by difference between normal atmospheric pressure and pressure in the system being measured. Yes, please next. So these are the different vacuum levels. Atmospheric pressure, that is 760 torr. Low vacuum, 760 torr to 25 torr. Medium vacuum, 25 torr to 10 to the power minus 3 torr. High vacuum, from 10 to the power minus 3 torr to 10 to the power minus 9 torr. Ultra high vacuum, 10 to the power minus 9 torr to 10 to the power minus 12 torr. And extremely high vacuum, more than that. Generally, that is not applicable in case of the integrated circuit fabrication. So these are the various vacuum levels. Yes, please go to the next slide. Yeah, now how the high vacuum is created inside the chamber. We have the different pumps. Different pumps are used. The starting pump is the roughing pump. That roughing pump is initially used to take out the material from the chamber via line is given. So you see in this figure, the roughing pump is started. When the work of roughing pump is completed, then the booster pump is used, and different valves are also used at suitable times. One valve is closed, other is open, something like that. And then high vacuum pumps like diffusion pumps are used to create the high vacuum in the chamber. So this is the typical vacuum pump arrangement to get the high vacuum inside the chamber. Chamber is on the extreme right. Yes, please, next. So these are the different vacuum pumps in order to get in industry. The oil vapor diffusion pump may be used to get the high vacuum in the range of 10 from RS7, but that is not that we cannot use in the integrated circuit fabrication. But use of vaporized oil to create high vacuum is less common due to contamination risk in integrated circuit fabrication. That is why in integrated circuit fabrication, for achieving ultra high vacuum, following pumps are used: either turbomolecular pumps, high speed rotating blades create vacuum by molecular momentum transfer that can be used, or cryogenic pump. That is, you can use the nitrogen, liquid nitrogen, the use of ultra cold temperature to freeze gases, achieving ultra high vacuum. Generally, in these pumps, nitrogen, liquid nitrogen is used. Yes, please, next. Vacuum pumps in integrated fabrication, integrated circuit fabrication. So first, roughing pump is used, then used to initially evacuate air from chambers before high vacuum pumps take over. Rotary vane pumps, oil sealed, commonly used for general vacuum application. Dry scroll pump, oil free, reducing contamination risk. That is very popular in integrated circuit application. Then high vacuum can be created, as I told you, by turbomolecular pump, cryogenic pumps, and diffusion pumps. Diffusion pumps are not used in integrated circuit application. Ultra high vacuum, for that, ion pumps and getter pumps are used. Yes, please, go to next. Application of vacuum pumps in semiconductor. These vacuum chambers are needed in lithography, etching, thin film deposition using CVD, PVD, etc. in ion implantation in molecular beam epitaxy. Varying vacuum pumps mean adjusting vacuum levels or shifting between different types of pumps depending on process requirement. This is crucial for achieving the right pressure condition for etching, deposition, and lithography. Yes, please, next. So this already we have discussed these things. Yes, please go to next. Yeah, last slide. So vacuum devices, one essential. In earlier electronics, vacuum tools become obsolete. They are not obsolete, still they are used in high power applications. Solid state devices, device high power powering materials like silicon. These devices offer high efficiency, utilization, reliability, performing modern technology, fabrication process, key steps such as oxidation, lithography, doping, deposition, and etching that require high vacuum. In advance of impact, continuous improvement in fabrication technology drives innovation, leading to faster, more powerful, and efficient electronic devices that shape the future of the computing and communication. Thank you very much. These are the references. Thank you very much for patient learning. Any questions from the audience?
Thank you so much, sir, for sharing your insights with us. We will now move to Q&A session. You can raise your hands or type your questions in the chat box.
I think now they are tired because already continuously they are listening to two speakers. That is patience listening. Yes, please, if you have any query.
So since there are no questions, I request Ishika to formally end this session. And thank you, sir, so much for joining us today. Thanks a lot.
Thank you very much.
Thank you so much, sir, for sharing your valuable insights on vacuum technology in IC fabrication. The session provided a foundational overview of the key principles of vacuum technology in integrated circuit fabrication and discussed the role of vacuum pump. As we conclude another insightful 6-day online ATAL faculty development program, we extend our heartfelt gratitude to everyone who made today's session a great success. A sincere thank you to our esteemed speaker, Professor V.V. Rao and Professor Muhammad Javed Siddiqui, for sharing their expertise on vacuum chambers and system design and vacuum technology in IC fabrication. Their session provided a comprehensive understanding of vacuum chamber construction, system optimization, and the critical role of vacuum technology in integrated circuit fabrication. The insights shared today have certainly deepened our knowledge of semiconductor manufacturing processes and their industrial applications. We also want to thank all our participants for their enthusiasm, engagement, and thought provoking questions. Your active participation makes this program more interactive and enriching. As we conclude day 3, let's take a look at what's coming up on day 4. Tomorrow, we continue our deep dive into advanced vacuum technologies with two exciting sessions. Session 7 from 6 p.m. to 7:30 p.m. Vacuum Technology in Packaging by Professor Chang Chung Lee, Professor at National Tsinghua University and CEO of Xiang Foundation of Science and Technology, Taiwan. He will provide insights into vacuum applications in semiconductor packaging, enhancing durability, reliability, and performance in device manufacturing. Our session 8